take your best judgment on the work first. And also, I think for the presentation, I was told that each presentation will have maybe about 15 minutes. So please think about maybe allowing a few minutes for questions. Okay, so if you have to go longer, I would say it's acceptable because I think some presentations will require some background introduction on the relevant work so that other students can appreciate the problem a little better. I think last week, Mr. Yu Liu had a very interesting talk related to but it's about, I think it's about the integer, the squares problem, and he presented some techniques that made a comparison. And tonight, I think we will have how many talks? But I know all of you, like some may work in groups, some may work in groups. So anyone wants to go first? I mean, I don't want to make some suggestions. I would say, whenever it's ready, I'm going to set it up and then try to go first so that we try to make the transition as smooth as possible. Okay, let's start. Okay, great. And okay, so I guess I will just distribute the evaluation sheet. As he finishes, then you can, of course, you want to write his name on the evaluation, the top portion of the evaluation page, and basically you don't need to write your name, but you want me to know that upon completion of all the presentation, you can put this to the top of the desk so that I can. Okay. This is only for one speaker, and for the next speaker, I will just pass another sheet. So don't worry.
Hey, you found my drive. That's cool. It's so nice when technology works, isn't it? It's getting there. Look, I filmed the class ahead of time and I put it on the projector. I hope that worked. It might not have worked. We will find out. Red. Cool. Optimization. Project. Tech. Project. Hey!
Okay, great.
That works. Oh, sure. Over this little clippy thing. Well, hello then. I suppose everybody can hear me now, I hope.
We can, so I'm sure that the video recording is probably fine.
Okay. How do I full screen that one? Okay. Well, hello, everybody. My name is written on the projector at the moment, so you can spell it correctly, or you can spell it incorrectly if you want. It doesn't matter to me. I'm the only one with remotely that name, so even if you spell it completely incorrectly, my error correction will be good enough to detect it. Yeah, so this is good. Good start. I'm working on the problem that Dr. Chen suggested that we could possibly work on. It's on taking an image and somehow sensing it and somehow quantizing it and getting it so that it's in a smaller form and then trying to reconstruct the original image using this smaller form version, this compressed version. And without further ado, I will begin, I suppose. This outline is also across the top, so you'll see it in more, as we go along. You'll have some idea of where we are. I guess that's readable, yeah. Okay, so we have. Do you have a question? Oh, that's up to you. Yeah, you have to be able to see the pictures. Okay. So since this is an optimization class, this is our optimization problem. It's minimize this top function subject to these constraints on the second line. And so in the next couple slides, I will explain what each of these things are. And the small, yes, I can actually. Okay. So suppose we have an image, X, capital X. It's in a matrix form as it is, right? So here we have 3 rows, we have 4 columns. And suppose that these numbers inside the matrix, these are the pixel values. that correspond to these elements, right? So if we have this function, this total variation function, it operates on an image, on a two-dimensional array, right? So you take an element xij, and this xi plus 1j is the element below it, and this one, j plus 1i, this is the element to the right of it. And so if you have this image, you can calculate the total variation of this image according to this objective function. So we will do that, or not yet. Okay, one more thing. So this objective function operates on the matrix, but our constraints operate on a vector, a lowercase x. And the lowercase x? That's this. If you have a capital X as a matrix, then the lowercase x is this vector. It's the matrix unrolled, right? Okay, so this will become important. This vector form will be very important soon. Okay.
So the total variation is defined in that way, right?
Total variation is defined on the matrix, the image, the two-dimensional array.
Yeah, but I see you consider the element beside that to the right of the x.
Yes.
But why you don't consider top of the left?
Because that was the formulation provided in the project. This objective function was given as, like this problem is given in the description that we're supposed to try to solve this.
Yeah, of course, a short explanation that you scan all the difference.
Oh yeah.
Presentation.
Oh yes,
So
yes.
it doesn't matter.
It doesn't really matter. Yeah. Right. Yes. That's a good point. This image actually, according to the way I laid it out, if you're on the right edge, it'll wrap, and if you're on the bottom edge, it'll wrap, and you have to iterate over every possible pixel anyway. So as Dr. Chen just said, that you will eventually get the variation to the left and above as well in some combination or other. Yeah, that's a good question.
I
Yeah.
wouldn't suggest you left that because
I-
usually the
I know, yeah.
assumption is that the image in the neighborhood, the pixel value shouldn't change a lot.
Right.
overall.
Right. I wrapped it for a specific reason,
Okay.
and it actually makes the formulation cleaner, I think.
Okay.
Yeah, so that's why I wrapped it. I think ideally, since the edges don't have any effect on the opposite edge, you should not wrap it in general, but I did anyway, because I like to do that. Okay, so this is the unrolled X. This is our vector. This capital X is the matrix, the original image. And so here, this is how we calculate the total variation. Now, before anybody asks, in the original formulation, there's a square root here in the total variation function. I ignored the square root because I was under the assumption a while ago that the square root would not change the location of this minimum, but it would change the height of the minimum, or the right. But I believe I'm mistaken, and that the square root actually does change the actual minimum.
Yeah, it changes
Yes.
the actual.
The location, it changes the location, yes. And but I
But you can propose a different
Yes.
objective function. That's more amenable
Mhm.
to
this
the solution.
if I ignore the square root, I get a very, very nice quadratic form,
Okay.
and that's why I like it. And so I did this. My problem is doing this with no square root there.
Okay.
So if this capital X is our actual image, and this function is our total variation, then this is how we calculate the total variation, and this is the total variation of this image X, right? And one thing that we should know is that this function is a summation, and if you wanted to do it in non-MATLAB world, you would use for loops or something. But in MATLAB world, you would like to do this in vector form. So this equation can be rewritten in vector form. And so that's what I will proceed to do in the next page. The first thing that you have to know is that this right element in the first sum, or the first binomial term, this is the original vector x, and this also is the original vector x. So with that in mind, I'm going to define two new vectors, x1 and x2. x1 is the original vector x, but it's been shifted a little bit, right? And then x2 is kind of like the original vector x, but it's been shifted in a different way. right? So if we actually want to obtain this vector and this vector, we have to look at the original image for a moment. If this is the original image, if we take this first row and move it to the bottom, and then unroll it, we will get this vector x1, right? And then in our original image, if we take this first column and move it to the right, and unroll that, you will get this vector x2, right? Okay. And then each of these vectors, x1 and x2, can be represented as a permutation matrix times the original x vector, because it's just a rearranging of all of the elements in the original x vector, right? So this t1 is known and this t2 is known, right? So if you have an image of a known size, then you know t1 and t2 automatically. Okay, that's important. So the first part of the problem is to show that this objective function is convex. And I chose to do it this way. If we go back a moment, a couple of slides, this is the objective function. And you can rewrite it in this form. So this is x1 minus x, and this is x2 minus x, right? And this is the norm of the stacked vector. So if we look here, if you take x1 minus x stacked with x2 minus x, this whole thing will give you that summation from the previous page, the total variation, right? And this x1 and this x2 we know are related to x because of this t1 and t2. So we can rewrite it that way. And then we can factor out x. And if we do that, we get a quadratic form in x. And we know by construction that C is positive semi-definite because it's like a squared kind of matrix kind of thing. So that means that this objective function is indeed convex. So any questions on that part?
So you got this result because you ignored.
Because I ignored the square root. Yes, precisely. Yeah. If you consider the square root, you can still do it. It's still convex. It's still convex. It's not a quadratic form like this because there's the square root somewhere, right? But I think maybe. Well, T1 and T2 you will get, but this transpose this will not be true. It won't be this kind of quadratic thing anymore.
Because I think in this case, one value that is T1 and T2 they are new.
Yes.
But once you have squared it,
Yes. Well, you'll still get an x1 and an x2 in that case, but if you ignore this left term, you will have to do some operation on this vector, this x1 minus x, x2 minus x. That's what you'll have to do. But norms also are convex, and this will be the sum of convex functions. But it's not going to be a quadratic form. So I have a feeling someone else who did this problem will have the correct formulation for this. But yeah, but anyway, so this is the objective function now can be written in this clean x transpose cx form. And C is defined for any size. So if you know the number of pixels in your original image, you know C is fixed. So you don't have to calculate that ever again. You just do it once. And then we have the interesting part of the problem, which is the constraint. And this x is the vector x. This A, capital A, is a matrix that we call the sensing matrix. And then this B is the observation vector. And I will, you can read the slides. What happens is this A will kind of pull out some of the information from the original image, and then you will get something that's AX. And you can compress this AX by quantizing its values, and you will get something that you transmit that's B, some compressed image. So A itself can pull out some features. A will reduce the size, or it will compress an image. So if you have an original image X, this AX can be smaller in size. It depends on your A. And so if you choose A correctly, you will get some form of image compression. And if you then quantize a little bit and you get a B, this will also offer you some more compression. So we have two different ways of playing with compression. And this is obviously convex because it's a norm of a linear function, so it's good. So I didn't work on that. But so I have in the next couple of slides 2 different sensing matrices and later on I have the results for using the 2 different sensing matrices. The first sensing matrix that I chose is something that I call the smoother or an averager or something. It has this type of a structure. And so if you know the input dimension, which is the number of pixels in your original image, and you know the output dimension, which is how much compression you want, you can kind of deterministically obtain this matrix. And you can specify some amount of overlap here if you want. It doesn't matter. That's up to you. But this matrix, if you multiply it by our original image, will give you this vector. So our original image had 12 components. This compressed version has only 5 values in it, 5 elements, right? So already we have compressed our image. This is one possible sensing matrix. And another possible sensing matrix is something that I call the random sampler, where you just pull random pixels from your original image. And so in this case, I happen to pull out these 5 pixels. So this offers the same amount of compression, but it carries slightly different information in it. So this is I didn't know it beforehand which one would look better or not, because how an image looks is very subjective. So I tried them both, and I have results for both.
What I suggested.
Oh, about that, it's CVX will not work with the FFT function of MATLAB, right? So if you have a way of the suggestion is to use, instead of this sensing matrix here, you use the discrete time Fourier transform matrix as your A, and you sample certain components from it. So the suggestion is to, instead of taking like AX, you do the Fourier transform of X.
The sample this image directly.
Yes.
Pixel domain separating for a transform.
Yes. Yes, but you first have to take the Fourier transform of the image, right? But the CVX, as it stands, has problems because you cannot do the Fourier transform of a CVX object, which you will need to use in order to optimize this many decision variables. And the reason I selected these 2 sensing matrices in particular is because both of them are sparse. And sparsity is important because if we have an image that's like 256 by 256, then that really means that our unrolled image is something like 65,000 elements. So if this A matrix had no compression in it, it would be 65,000 by 65,000. And that's more than terabytes of space just to store the matrix itself, let alone to do operations with it. But if it's sparse, you can say, all right, I want my sparse matrix to have at most 2 times the number of pixels in my original image. So that's manageable. If you have 65,000, your sparse matrix will have only 120-some thousand elements in it. It'll still be the proper size. It'll just be very sparse. And so MATLAB, fortunately, has a sparse matrix, like objects that you can use. So both of these matrices are sparse. And if it were not the case, then this problem would not be feasible in any way, shape, or form. Unless, of course, if you can do, like an FFT is an algorithmic thing, so you don't actually need the whole A matrix. So that would be another way of doing it. If you can find some function that operates on CVX objects, then by all means use that. It'll be better than storing this entire matrix at all times. But in my case, I was just doing the linear transformation using a matrix. Okay, so we've talked about now the sensing matrix and how this can offer some compression. The other step is to offer some quantization. So here, if we use the smoothing matrix on our vector x, we get this, but we can quantize this into some like binned values. So if you want to represent this b, each element only takes 2 bits because each element can only take 1 of 4 values here, and you only need 2 bits for that. So even though you get, after the linear transformation, AX, this is still kind of big, depending on the amount of information in each element of this vector. So you can quantize it further and get even more compression out of it. And so if you have AX, you have B, then you get some combined compression. And if we go back to our formulation really quickly, this epsilon is the difference between the unquantized version and the quantized version. This is the error. And so if this epsilon, if you set it too small, there will be no x that matches this, this quantized form. So, and if you set it too big, then any x that you set will be whatever it is. You know, there won't be any optimization there. So if you have to select this epsilon appropriately for every problem. And so you can calculate the true quantization error in this form. And in my code, I made it like 1.2 times the true error is my epsilon that I used. Something of the sort. So we have now all of the components of our original formulation minus the square root. If we go back to here, to here. Okay, so we now know that this word equivalent is not correct. It should be an alternative. This is an alternative. We have our convex problem. We have the convex objective function. We have convex constraints. And we have them in very nice vector form. So the only thing left to do is to try it and to see how it works. And that's what I did. Okay, I came up with 2 or 3 different scenarios. One is that we assume no quantization, and we just do image compression by reducing the number of pixels, or by having our A matrix have fewer rows than columns. Another way you can compress the image is if you know the size of A, then you can use varying levels of quantization to get different compression levels. And then finally, I tried varying both and seeing how they worked. And so here we go, pictures. This is kind of blurry on the projector. It's a little sharper on the screen, but you'll have to pretend that you can see it correctly. This image in the top left is the original Pepper's image. It's 256 by 256. And on the projector, it doesn't look too sharp, but here on the screen, it is sharp. So if you have a good screen, you'll see it's sharp. In this scenario, I used the smoothing matrix that I defined a couple slides earlier. This image has half of the number of pixels as the original image. This image has 1/4 the number of pixels, and this image has 1/10 the number of pixels. And so these are reconstructed images. On the screen, this image is significantly blurrier than this image, say, on this screen. I don't know, on the projector, I don't know if you can see it too well. You can see it a little bit? Yeah. So here, you can see that if you only remove half of the pixels, and no quantization, the compression is pretty acceptable, I think. Like that, I mean, judging the goodness of this is very subjective. But in my view, that one's pretty good. Even this one where you lose 1/4 of the image is pretty good. It's not bad. This is without quantization, yes. But it's still, this image is 1/4 the size of this one. Yeah. And I think actually, since I see a delay in the mouse, that means that this feed is the same as the feed that we would be sending to Stennis. It's not a direct feed from this. I don't know if we can change it. It'll make the resolution better.
I don't know.
Can we ask? Because that would help for.
I think last time probably they tried. It doesn't really improve.
No, it does though, because one of them is 640 by 480 because it's presented on the TV screen, and the other one is the actual resolution 1024 by 768. This is not the correct resolution at the moment for matching the computer. It's matching the stream right now.
For the video phone?
Yes.
Or the video screen?
Yes.
Well,
But on the projector, we can at least get the better view.
you guys can still try on this.
Yes. Yeah, but we can actually get this to be as sharp and as responsive as it is here. Because even right now, when I move the mouse, there's a half-second delay because that feed and this feed are not the same. Yeah.
I'm not worried about that because I think we have a very long presentation.
Yeah, but it might just be like pushing a couple buttons here.
Probably not that important, I guess.
Well, anyway, but I was thinking since a few of us have things where you need to do pixel peeping, it might be important. But anyway, if you're okay with this, then that's fine. So this is using the smoothing matrix. Sorry for the digression. Here, I tried the same thing using this random sampling matrix. This is, again, half size, quarter size, and 1/10 size. Again, the difference is kind of subjective. This one, it loses some of the edge information, like it kind of comes out fuzzy almost, but it's not blurry. The other one is blurry, but it has its edges kind of roughly in the right places. And so this is all with no quantization. The next thing to try is assume we fix our using half the number of pixels and we quantize the image. So here in the center, we have half the number of pixels and each pixel uses only 2 bits. Originally, we use 8 bits per pixel. Sorry, we use 8 bits? 4 bits? 8 bits. We use 8 bits per pixel. 8 bits, right. 8 bits, 8 bits. So this image on the far right is half the number of pixels and half the pixel depth, the color depth. So this image on the far right is 1/4 the size of the original image, which is on the left. And this image in the center is 1/8 the original size. And but quantization, as you can see, it has some serious effects if you quantize too low. So if you only use 2 bits for grayscale, doesn't look too good. But this is using the smoothing matrix. And if you look closely, you can see kind of the gradation here, or the gradients. They're kind of sharply defined because of the quantization and also because of the way the smoothing works. And again, same example using the random sampling matrix. The quantized one, the 2-bit quantized still looks kind of rough. 4 bits here looks pretty good. But if we flip back and forth, they look identical on the projector. Okay. Can you see a difference between these two? If I flip back and forth on the far right image? Yeah? Anyway, so the sensing matrix here is not as important as it is on the computer screen. Yeah, so this image has, as I said, 1/4 the amount of information stored as this one does. But it still looks pretty good, I think. So subjective again. And here, this is just the effect of quantization. This is just the effect of the size. My mistake. This is using the smoothing matrix, this is the original image, the center is the full size with 4 bits, and this is half size with 4 bits. So again, this is half the size of this, and this is 1/4 the size of the original. And the results look pretty okay, I think, using the smoothing matrix. And this is with the random sampling matrix. They still look pretty okay on the screen, yeah. And finally, we have the full 512 by 512 boat image using half the number of pixels and half the bit depth per pixel, or half the color depth per pixel. And that's the result. This running CVX on an image that's 512 by 512 takes maybe 45 minutes or so to complete this, yeah. But the other ones take maybe like 10 minutes, give or take, yeah. And that's it. So this method of compression is this is the discussion. The method of compression is intensive computationally, certainly. It offers pretty good results, but this is especially good considering we don't actually take any useful information from the image. We're just kind of random sampling, or we're kind of yeah.
Image content, not image content specific.
Right. It's just a general, yes, this is true. So this is a very general algorithm, so in that sense it's good. For image compression in particular, it's not, you could probably do better if you,
If you have the image, you just compress this image, then you can do much better.
Well, no, what I'm thinking is, like if MP3, for example, which is an audio compression, it uses some knowledge on the way ears work to remove some information already. So if you have some sort of model for image, like what pieces are not useful anyway, that will offer some better compression for the image domain in particular. Of course, you can compress a specific image more, but in general, this algorithm will not be as good on images as an image-specific algorithm would be. But this is a more general algorithm. So there's a trade-off there. On the screen, on the projector, you can't really see the difference between the sparsing matrices. The sensing matrices, not the sparse, sorry, the sensing matrices. But on the actual presentation, if you look closely, you will see a very stark difference.
And of course,
there.
you can even make it sharper in terms of compression ratio
Oh, yeah.
at least to see the difference in the distortion.
Yes. I tried, the most severe that I did was 1/10 with no compression.
Okay.
And it was, you saw the results, it was kind of like, whatever, yeah. But all in all, that's the work that I did, and these are the results that I got. Does anybody have any questions, comments? Any curiosities about life or anything? No? Okay.
Thank you very much.
Sure.
And now we go. Okay, so Gandhi will do a presentation.
Yeah,
And also, I
same.
will distribute with a new evaluation sheet. And if someone already finished, then later let out.
Yeah, I thought it was all right. Okay, you can have our friend and our friend's companion. They come in a pair. This is important. Here you go. Put that there. And it's here. Okay. Although it's at a funny angle. I don't know if you've used this computer before. Okay. It should.
Right,
It
thank
popped
you.
up. Yeah. Good luck.
Thank you.
Yeah, this is really not right on this projector. Can we change it now that we're between presentations? Can you ask them if they can change it? It should be a quick fix.
Change to the.
Change what's on the projector to what is on the computer.
Okay, sure, thanks.
Yeah.
This will may not be loud. Thank you.
Right now, on the projector is the stream instead of the actual computer feed. Is there a way to solve that?
Like, it's not showing what's on the computer right now?
No, it shows what's on the computer, but it shows it passing through the stream. Like if you move
Yeah,
the mouse
that-
here,
Yeah, that's what we were
this
checking
is,
on.
This is significantly delayed.
Yeah.
I know this is possible to mirror this.
It is, we're missing that connection. Something we were checking on that just earlier.
Yeah.
We're lacking that connection, and I was checking with my
Huh.
boss on it. And
So you can't do it.
yeah, no, not currently. Even
Huh.
last week we had an issue with it, and
Okay, because I know it's worked before, but we're doing like things where you need to
I think
pixel
for the
peep,
past
so
2
it's,
weeks,
You need to
you
what?
probably could have had that.
we need to pixel peep, looking at like sharp images, you know?
Because
Oh,
So
right.
640 by
it
480 is not
It
quite
would be,
enough.
yeah, of course, it would be nice.
I
but,
gotcha.
Better resolution.
Yeah.
It's okay. What you added.
let's make sure. Let me check something real quick.
Okay, thank you.
Mm-hmm.
Okay, and for the evaluation sheet, sorry about the time
That looks
control.
good.
That is
Is it responsive?
Oh wow, yeah, that's
Okay.
Okay.
That's the correct speed.
all right. Awesome.
Thank you.
Oh,
No problem.
thanks.
Great.
Did I lose my pencil? Did you take my pencil?
Okay, good evening, everyone. My presentation, my term project is same as Rustin's, the image recovery. As we see the outline here, we have pretty much the same topic. From the project background, the CVX software, and as then go by the image reconstruction, I have a few examples, compare the pictures, and also I have some discussions to see the behind scenes, what is behind. Okay, the project here is given by Dr. Chen in the term project on the blackboard. The goal is to, I think Rustin said most of the basic stuff, so I just skip here and focus on the differences. Okay, the next one, next page, I put the data flow here. This is actually image compressing and decompressing. So from the source image, we did the reshape to the vector and convert by the linear transform, then quantization, make quantization, my English, and make it shorter, make it shorter and fewer space, storage space. For the decompression, we go reversely. We use optimization to get the source image as much as possible, the X hat, and recover by using the reshape. So this is the data flow. Keep this in mind, we while we're doing the optimization, we use the CVX software. It is designed by this guy. I went to his homepage. I feel he's good. He didn't organize a big group, but just completed this. I'm not sure how many people work for him, but this. Yeah.
Well, he has a few groups called there as well. Yeah, one is this kind of optimization, the other is about the linear matrix quality and also the
Yes.
working control field. He has a lot of control background.
Yeah, he's very good at this, and his research very focused on this very much. Go very deep, I believe. So this installation is pretty easy. Just unzip and run setup, and then the code is in this format. It's quite simple with some initialization. Inside the CVX, you define the variable, you minimize what you minimize the goal and subject to what. So quite straightforward, like what we write on the book. Okay. Right now, the problem analysis is how I derived this is a convex problem. I use the square root. The Rustin suggests us, Rustin introduced this. I just put it in an image. The xi j plus 1 is on the right side and below. So this fx is square root of two differences of squares of two differences. The derivative, we got like this. And the second order derivative, it is always more than 0. And there are two conditions. If these 2 points are exactly the same, I'm sorry, I didn't make this, but because of the screen. Okay, because of the screen, this is not equal. This is not equal. It is sharper than on this screen. So when these 2 pixels are not equal, these values are different. When they are different, I plotted the fx. You see the first order derivative is less than 0. This is going down. And at the bottom is 0 and going up. So this is a convex problem for the single fx. So as we know, the sum of the convex program is still a convex program. So a set of
a linear combination of convex function is convex, but only when you have positive coefficient. In this case, for the sum of convex functions.
yes, over. Yes, that's what I believe. So also in other instance, when 2 pixels are exact same, this column feature has a very good performance with respect to minimize the x. So when 2 pixels are so close, I put this in another page. I have another page to see the difference about this function. Okay, let's move on. So for the entire pixel, we have a graphical understanding. Means let's suppose 2 pixels are extracted from the original picture. We have these 2 pixels fixed. The best way to minimize the TVX, if we think it intuitively, is just make it the smallest way. We'll minimize this TVX because of keep the difference, side-by-side difference minimized. So this is the intuitive graphical understanding. Okay. The next is how we calculate this TVX. The TVX are different than Rustin's, but thank you for Rustin. We discussed this. This was his idea to put a matrix and put indices of the matrix. This is much faster than I did before. So with this, we can use the norms to calculate the difference, because the first one is the one dimension, The second one is another dimension of a vector. All these vectors, they will be calculated norms first and then sum up. So this is efficient enough in the MATLAB. And these norms can be accepted by the CVX software. Okay, so it's pretty much the same. I just put it in another way with Rustins. During the image reconstruction, we have some problems. The one problem, the FFT doesn't work at CVX software. It just not recognized. It says no library for the CVX. So we have to use that keep a matrix inside. But how to construct the matrix, I use the different way. I make it sparse, also make it random. I just use a random generation to make the randomized I and j and put them into the matrix phi. This matrix phi, the density of this matrix phi can be defined how many of the elements here. Here I put n numbers, so which means giving example of this is 3 by 6, n is 6. So I just put 6 numbers inside here. Okay. The next problem is how we choose the epsilon. Epsilon is choosing, it cannot be too small or too big. If it is too big, I'm sorry, this one is missing. I guess it's my fault. But if it is too big, there are just too many possible or feasible points that take a very long time to find out, to sort out. Also may not be exactly recover the previous image. But if it is too small, I found sometimes no feasible result. It just CVX just report unbounded or some unfeasible, not solved, something like that. So while we select the best result is the norm of x, of this difference. Here the bx, this 2x, I put it differently. This x image, it means the source image of the pixel, the source values. During the quantizing, we check the arrow value and take the norm, put it in epsilon. The first one, during the optimization, we just try different feasible axes, see how the constraints is, make sure it's less than epsilon. Okay, let's go to some pictures. Before that, the out of memory problem, I tried to divide it into sectors. I still, even today, I cannot figure out how Rustin did that. How you make the conversion 256 to 256. The highest dimension I can reach is 192 by 192. That's it. Maybe or maybe not. Maybe he used different metrics. I need to find out how he did it differently. But anyway, with that, I have to cut it into pieces and do one by one, like this. Okay. However, when I do this, I found a problem. It's just the edges, because the optimization is done within that small sector, so it cannot examine the differences across the boundaries. That makes some problem on the boundary. Okay, here is the code, how I wrote it. As you see, this is even simpler than the example, than the given example. It just minimize the function of TVX, the sum norms, with the subject to the function. Okay, here is just the example. When we give some, the image is still very good. I noticed for this algorithm, because this algorithm assumed minimize the change across the points. So this algorithm works better for those smallest pictures, like the peppers. I tried the peppers because they are fewer lines. So even with same parameters, for those small picture, it works better.
This picture is, this image was chosen because of the testing for the testing purpose to see if you could preserve it.
Yes, yes. So some of the is preserved well, but those lines are lost somewhere. Okay. There are some. Okay, here we go, picture by picture. The beauty girl. This one, I cut this beauty girl into 64 pieces and finish that. This page is in order to compare what's the difference between two different sets of parameters. I had the k value, which is the size of B, fewer than the new one, the right one. And also the bin value is slightly different. You can see the difference. Still, especially those details, the health are lost much. For other small area, it's good.
Also, it's interesting to observe when you calculate these these unoptimized pixels usually are reconstructed somehow very different from the adjacent.
Yes. Because this picture is occupied about 4 hours of the computation time. So later I found the solution to solve this to great extent, but I didn't redo this image. So I could do better with improved method. Yes, please. Okay, the pixels is 32K is 12% of the original pixel. It's not like I picked up which pixel.
Oh, the bin is maybe 64 levels.
Oh,
Yes.
it's not the number of like cuts in the image, is it?
Back to your question, here is the file, right? This file is 3 by 6. So it converts, the source vector is 6 dimensions. It converts 6 dimensions to 3 dimensions, which is 50% reduced. What you asked the question, that was 12% of originally. So this matrix is about 1 by 12, that ratio. So it not exactly how many points I sampled. It's just compress the source n into 1/12 of the 12% of the source. You can say that maybe, but not exactly. Okay, so back to any other questions? Thanks. Okay.
I think the skill can explain what the rest you have about the quantization.
Is that in the quantization level? Or is it
Yes,
number
because in the code, the code is sort of given by Dr. Chen. He used this name as bin. How many bins you put?
Yeah, so this is 6 bits here on the left.
Yes,
7 bits
6
on the right.
bits.
Okay.
It is 7 bits.
6 bits per pixel.
6 bits, yes.
You can say 64 levels, which means that with 2 of the
Right.
width, you
Yeah.
represent the pixel.
So it's a 6 bit per
Mhm.
pixel
On that. Okay.
on the left, yeah, and 7
Yes.
on the right.
Yes.
Yeah.
Okay.
I thought this bin was somehow number of cuts in the bin, but no. It's
No,
quantization.
it's not. It's quantization. It's not
Okay.
the how many cuts.
Right.
Okay. Okay. This picture we show the difference among the difference between the bin value because all other parameters are exactly the same. This picture, this graph doesn't show very well difference. Maybe I should have switched another because of the inverter. Okay, here we go. This page, I say small pictures has a better result. Only besides those details are loosened. Okay, here another example, just how we compress. When especially those flat points, they are good, but those with details are lost a little. Okay, here I found some interesting thing, just the difference between two forms of the objective function, with square root or without square root. On the left is my code. It's running my code with all the same parameters, but just the different objective function without the square root. The right side has a square root. I use different way to put it into CVX, but they are all vector operations. The left one, you see on the flat surface, it's not so flat anymore. And on the right, it recovers the white point very well. So this is different. But why? Do you have any idea why? I try to explain, and maybe not exactly the answer, but please see if this is right. I try to answer by using, okay, this presentation is, okay, anyway, we can try to figure out the line here. Because these two functions having different features of the objective function. You see, maybe you try your best. The blue line is in the middle. The blue line is on top of the red lines. On the side, the blue line is below the red line. So this is when two pixels are having big difference, meaning these two pixels, if they are not the same, both functions has a small button in the middle, which leads quite hard for this optimization to work, because the flatter, the harder to choose the x. I remember one project we did is the gradient works through the alleys. So when it has a flat button, it's quite hard to find the optimal solution. So this is the same. But for our picture, some of especially those white areas, most of the pixels are having the same values. Especially they are same or very, very close. These two functions are quite different. Without the square root, this function still a flat button. But with the square root, the function has a very sharp button. I believe because of this, the optimization work better. This is my belief. I'm quite sure this is right. But how about you thinking? Any question?
If you believe it is right, why still you need other students talking to the
Okay, this is the mistake. Okay. The next picture, we show how I solve the edges. The edges because of the function. Because of the pixel sampling matrix, this index, just like Rustin did, I did the same way I learned from him. The edges, if the edges are wrapped up, you see this is the index. We use the right side of this pixel to minus the x, the number 4 pixel to minus number 1. This is okay because it measures two different values side by side. But the last one, if we use number 1 to minus number 7, which means it is wrapped up, try to compare this point to this point. This is too bad if these 2 points, this side by side have big difference. So, but I just change it a little bit, make it the left side. So the last column of this function is compared with the second last column. So with this modification, the picture is improved a lot. The borders are all gone. You can see here, this picture is not very well, but you can use. Can you manage it to see there is a straight line inside here? But this one has no straight line. Okay. Okay, so that's all my presentation. That's all my slides. Here I got some summary. This is a convex program. Also, the CVX is applied. The CVX is quite powerful with respect to the high dimension data. Like for this case, it's more than 10,000 decision variables. It can be solved, and the format is quite easy understanding. Also, there are certain limitations. Some function cannot be working on civics. We have to, for real question, we have to change some function or adapt it to. And also, this several different parameters has several different impacts to the image recovery. In future, we may think the computational complexity. At least I need to find out how Rustin did that after this presentation. And thank you for Dr. Chen and Rustin of this. Thank you. Yes, any else?
So typically, how long does it take to run one optimization for 256 by 256 feet?
Around, for my case, it's around 1 hour.
It takes 1 hour to complete.
Yeah. Yes.
And on what kind of
It's just an average laptop or desktop.
like on your laptop?
2 gigahertz, dual core.
Oh, that's not bad.
That's not bad.
Configuration is not bad.
Not bad.
It takes very long.
Yes.
256 by 256 for me was 10 minutes or so.
Uh-huh.
Yeah, running on my laptop.
I must be doing something wrong with mine still very quickly.
Yeah. Well, maybe you have some ideas that we don't. We'll see.
Okay, thanks.
Okay, who's next?
Yeah, I think that way is the voice station.
Where am I plugging into? Dr. Chen. Where's the computer?
Oh, yeah.
Or, oh, okay. Seriously? Do we have a pointer or anything hooked up, or was that?
I was just using the mouse.
No, okay.
With you.
If you want to have
It doesn't matter. I was just wondering if the clicker was actually hooked up or not. Was it a problem? Okay. Lippy?
Pointing at and get our attention.
All right, so I did the same thing as Rustin and Gang Lu. Basically, that same image reconstruction problem. So really, we already know that sensing matrix A, hopefully. There are definitely some issues with it. And then we get this B vector, where ideally the relationship between A, B, and X is this. It's the sensing matrix times your actual elements gives you B. But there's some error involved, and we quantize, so there's a little bit of round off in different things. So we want to optimize define X, which for me is the column-wise ordering of them. So you have just all the, row 1, row 2, row 3 for all the column 1, and it'd just be stacked up like that. So then the problem is to take this total variation, which we've seen about 2 times already, and basically minimize that subject to this constraint right here to minimize the error. Oh, actually, yeah, might as well go through it. Anyway, so is this going to make this draw in here or something? It might. Good. No. Okay. Sweet. Yeah, so just real quick. Basically, this is like row 1, just like to the end of row 1. This is like row n all the way down here. So that's basically what, that didn't work. Last column. So you basically end up with that. And for me, to calculate that total variation, essentially what I did was, if this is a little x right here, I took one where I moved this last row element all the way to the beginning. So that shifts everyone down by 1. And then I took another one where I moved the first column to the end. Now you have column 2 all the way to the last column. That shifts everyone down by the number of rows, essentially. So then you subtract x from each one of those, and you take the norms, and you sum it all back up. Okay, so real quick, this is a second order cone program, and the main reason for it was essentially that constraint that we saw on the last page, the norm of b minus ax, essentially gives you something that looks like this nice little ice cream cone. And you can see right here, cone's just the general definition of a unit cone's right here. So you have that norm of this this u element, which has a dimension of, well, this is a dimension n cone. So u has a dimension of n minus 1, and then v has a dimension just of 1. And that's the definition of it. Okay, so for CVX, it doesn't like that square root at all. So essentially what you end up needing to do, I pretty much figured out the same thing that Gang Lu did. There's that norms function, and I essentially looked at this as being just the norm of the gradient. You basically have a discretized gradient, have these guys which are like this minus the original x is your sort of like your partial, just your partial values. Okay, so then when you actually go to run it, just wanted to basically, this is the b from the a function that was provided. And you get basically whatever, it was the FFT that was applied to it, and you get all these values to it. Then you go quantize it, and you get this thing that looks very flat. So you got, these are our bins right here. So this is the infamous boat image. And this was the image that we were given. And then essentially, I took that b from the last page, I flipped it around through the AT function just to see what it would get. And this is essentially what I got out of it. It's kind of nasty looking, actually. And ideally, you get this image, which looks pretty blurred out. Does anyone have any questions? Right there. Yeah. How do you write the?
Yeah, you try to use that the square root doesn't work for.
Sorry, this is the norm of the gradient.
The norm of the
Yeah.
gradient, be accepted in CVX.
the gradient's just this minus this and that minus that gives you just a two column vector or a 2-column matrix of n elements. And you take that norms function, tell it to work along essentially the second dimension, I think, and it'll return out a n by 1 vector for you. And you just tell MATLAB to do the sums on it. Since we're just dealing with pixel values, so they're all 1 apart. So basically subtracting pixels that are next to each other gives you that partial difference. Normally what? You'd say what? Just the partial gradient for something would be what, like, you'd have f of x minus f of x plus just a little number all over a little number, right? But for us, that's 1. It's pixels and it's discrete. So it's a pixel value minus the next pixel value over 1. So essentially that's the gradient. And it works because we're working with a discrete image.
Very great. Thank you very much.
Do I plug in the jump drive?
Yeah, right in the extension cable. I have that problem too.
Dr. Chen, do I have to wear the microphone? I think I'm sufficiently loud without a microphone on.
Well, I mean, it's up to you. But
Okay, because I tend. Okay, I'm going to talk. I'm the 4th person to do this topic. There was a lot of bumps and bruises along the way, but after seeing some of my colleagues present, hopefully I know of a way to better improve my work. So that's my title, Mesh Compression Recovery via Total Normalization. So what is total normalization? It really depends on who's being asked.
can you make it full screen?
Oh, sorry, forgot about that. Depends on who's being asked. So I have a variety of references at the end. According to one author, this is what the total variation is, which is the gradient of f over its domain omega. And here they use the L1 norm of the gradient as opposed to our project where we had to use the L2 norm.
You don't have to, but that's one suggestion.
Yes.
You can use L1 norm as alternative objective. Like Wesley already changed that square root to without it.
I don't recall why, but the L2 norm is preferred, something I think to do with integration. But I don't recall off the top. Okay, another definition. Total variation is a useful statistic that measures the quality of an image. Clean images tend to have a low total variation value. Noisy images tend to have a high total variation value. So by cleaning up, we clean up noisy images by trying to minimize the total variation value. And we either call this TV denoising or TV minimization. Okay, I was stuck on this issue for a while. What does the formula mean specifically? What got me stuck specifically was the wraparound issue. Because I knew that when you go to the edges, if you have a matrix here, when you go over here, I didn't know what to do. So eventually I found examples, which I share with you now. Now for the 1D norm, for the 1D total variation, it's not an issue. And also if you vary the indices, backwards, forwards will be the same. So what you do is you take your function values, adjacent function values, you subtract them, take the absolute value, if this is the definition of our total variation. So in this particular example, if you do the total variation, we get 3. Moving on, if you change the indices, there will still be no change in the total variation in the one-dimensional case. Reason being, this is absolute value, so whatever way you move it, if it's F4 minus F5, it wouldn't make a difference. Even if you use squared, it also wouldn't have made a difference if you took the norm. Below is a two-dimensional formula used. For this particular example I'm going to illustrate, the indices start from ij equals 2, and they go up to the maximum number of rows and the maximum number of columns. So you can think of it being like this. That these this row and this column would be left out when calculating the total variation. So for this matrix, I hope you can see the arrows. I tried to see the arrows of how each element tries to compute the difference between its neighbors. If you compute the total variation of this matrix, you get 12. Now, if you change the indices, meaning if you start from here and you go down like this, because I'm not using wraparound, you will get a different result for total variation. So if you wrap it around like this, the final result would have been 4. And here, just for the notation, u, x, y is just an element in the matrix. M is the maximum number of columns, n is the maximum number of rows. So total, depending on how you do it, it matters which way you start from, how you count your indices. All right, for our particular problem, we use this formula over here. And I stuck with the square root, the norm of it. And the rows that are going to be left out, the row and column that was left out was these bottom two over here when I computed the total variation. We also have this constraint that previous people before me explained. Now, I've tried doing this using a variety of approaches. Most of them failed because for MATLAB-specific algorithms, they like to build huge matrices. Like fmin search, fmin con, their matrices are huge and you get an out-of-memory error. Now, if you want, you can go within the source code of these functions and change the implementation from a full matrix to a sparse matrix. I think that would help, but I didn't bother trying to do that. I also tried to consider using a modified conjugate gradient from previous assignments. One of the previous assignments, I did a conjugate gradient that worked pretty fast. But eventually, after I didn't know how to represent the constraints properly in this context, I just abandoned it and I stuck with CVX. All right, this is from the author's website of CVX, what CVX is. It supports disciplined convex programming. You have to specify your convex program in a certain way. And if you recast your geometric programs into a convex program, it'll be able to handle them as well. Okay, so what did I do for a CVX algorithm? First, I utilized Dr. Chen's code to generate the observation vector B. Now, I know now why my results aren't as good as some other people. I choose the number of bins to be too small. Now I know number of bins correspond to the number of bits per pixel. Before, it was just something black box. Whatever it was there, just use it. Okay, Now, this might have been an oversimplification. The only reason why I did this was I was afraid this objective, I don't understand the math that well, but I was afraid this objective function might behave differently in the Fourier domain. Does it behave the same regardless of what domain you're in, Dr. Chen?
I'm sorry, I think
Does this function behave differently if you're in the Fourier domain? Does it itself need to be transformed?
well, this is mainly just of image.
Uh-huh.
The underlying assumption is that the neighborhood pixels shouldn't have too much change in the pixel values to make it simple. Like overall, if you have an image, you wouldn't expect the neighborhood pixels have large variations.
I get that, but in the Fourier domain, the question is, it shouldn't make a difference.
Well, I don't know.
There's no reason why adjacent frequencies would have similar content.
Well, because of that suspicion I have whether this objective function would behave properly in the Fourier domain, I actually took the observation vector. Now, whether or not I was supposed to do that is a different story. I took the observation vector and I used the adjoint Fourier transform to get a 65,536 by 1 vector.
Okay, I mean, I don't know later how you're going to proceed from there.
Okay. And I also picked my sense matrix to be the identity matrix for now. I've tried other things before, and some sense matrices simply gave me garbage, so this one worked for me. All right, this is my MATLAB code, and it runs pretty quickly. So after hearing some of my colleagues taking maybe 4 hours or something, I'm worried I was doing something wrong. So I believe this here, everything is correct. Now, what I differ from other people is in my definition of my total variation function. And here the input, B, is the observation vector that has been taken from the Fourier domain back to the regular coordinate system. A is the sense matrix. In this case, it's the identity matrix. E is the norm of the error vector. I just took the norm and used that as my E. Now, this is my total variation function. Now, CVX doesn't complain about this, even though I have square root in it. So what I did is right now, passing in x right now is a column vector. When I go to my function, it checks whether it received a stacked vector or a matrix. If it received a stacked vector, before I move on, I reshape my matrix. I reshape my column vector using the reshape command, and I obtain a matrix. Now, I iterate over this matrix, and I try to apply this formula over here. I try to apply this formula over here, iterating one element over the other. Given this is MATLAB, I probably could have used vectors, but this was a pretty straightforward implementation to implement. And I stop at rows -1 and columns -1 so that I don't get index out of bounds when I hit these ends over here. And again, MATLAB had no problem with this whatsoever. Okay, I also performed some comparison studies. I was thinking this is a convoluted way of doing things. I was trying to think if I did a simple approach, how would it compare against this approach here? Now, these comparison studies are not going to be valid mainly because the number of bins I used was too small. Now that I know what binning is used for better, I'm going to rerun these comparison studies and choose a larger bin size. So I use 2 scenarios. One of them is half the number of pixels. The other one is a fourth. And I compared them with 2 pure discretization approaches. One approach, discretize 4, given your matrix here, given your, let's see, I took each 2x2 matrix and I replaced them with the average. That's what I did with this function. Now for the function, so this discretize 4 is to be compared for the 1/4 total number of pixels approach. I also have a call called discretize 2, where I take a 1x2 column vector wait. I take xy, xc I mean, and I replace them with the average. And I compare this approach with the CVX approach. Okay, on the left is my discretized 4 image. In the middle is the original image, and on the right is my CVX optimization using the identity matrix as my sense matrix. Now this poor performance most likely is going to be attributed to the low number of bins. I also calculated some scores for them. I calculate the RSS score, which is the residual sum of squares. So I took the ground truth and residual sum of squares. For column vectors, it's x minus y transpose x minus y. So naturally, before I use these algorithms, I first stacked my vectors. And then I ran that code. So for discrete 4, the RSS score is residual sum of squares is 0.0048. And here for residual sum of squares, small is better. And for CVX, the one that generated this image, my residual sum of square was 0.0961. So one might think that discretization, as I have introduced earlier, might be better than CVX, but then again, you have to take it with a grain of salt. These results are for CVX using 10 bins. If the number of bins were to increase, then the results may differ. I also calculated total variation of each image, and the discretized version has a lower score than the CVX version. This is for results for half the number of samples, and this is discretized 2, the one that takes column vectors. The one in the middle is the original image. The one on the right is what I obtained from CVX. For discretized 2, the RSS score is very small. Now this surprised me here. The total variation is actually larger than discretized 4. I wasn't expecting to see this value. CVX, the RSS score is over here, and the total variation score is larger. So what I intend to do before I submit any report, construct a useful sense matrix other than the identity matrix. That would be a first order of business. Dr. Chen provided me yesterday with a very nice algorithm. I'd like to see how it compares against what I've done so far. Analyze with a higher number of bits. This is probably why my performance may have been poor. And stay in the Fourier domain. And again, the reason why I left the Fourier domain is because I was worried that the optimization function might function differently in the Fourier domain as opposed to the regular domain. Here are my references that I used for this talk. Any questions? Yes?
How long did it take to run? Like how many iterations?
Less than a minute.
Okay.
Like 4 or 5 iterations and then it's done.
I think if you take B,
Uh-huh.
do the inverse Fourier transform on B, or the adjoint or the AT function that you
Yes.
use, right? You get a vector that's
65.
same length as x, right?
Yes.
So that's more or less already determining x completely,
I see.
right? Because I think
Well, with the identity matrix, if you pass identity matrix,
Yeah, but
X is going to be B if you
more or less-
pass
more or less,
identity.
You have so many constraints that all of your pixels of x are known already when you do
Uh-huh.
that formulation. I think the reason that happens is because when you take, you have your original image x, you take the Fourier transform, you take some of its components, right?
Uh-huh.
When you do the inverse transformation, you have to assume some value for the components that you left out.
Yes.
And I think if you use 0 for all of them, you will get an image that looks like your deconstructed image.
Uh-huh.
right? And that's the only way this matrix will be invertible, is if you fill in the remaining values. But if you do that, then X is already determined, and you're not really doing an optimization problem at that point.
Well, putting zero won't work.
I know, but that's why he got the result that he did, I think, and that's why it's such a quick thing. Because this transformation that you're doing is losing information, so it's not really invertible,
Mm-hmm.
right?
Yeah.
Can you go back to,
Yeah, this one on the right.
yeah, see that looks like that one where I did AT on the feedback.
Yeah, they'll basically be the same.
But I think you need to do A of X minus B instead of X minus AT B,
Uh-huh.
because otherwise you're not gonna have an optimization problem if you do it the way you did, because it's determined more or less.
Easy fix. The only reason why I did ATB in the first place was because I was worried that the optimization function might behave differently in the Fourier domain. Because I'm not that familiar with it, but I would think that if you transfer your coordinates from regular to Fourier domain, I would think maybe your optimization function should be translated accordingly as well.
I don't know about the total variation. I'm sure you can define total variation in the frequency domain if you want. It might be different.
Yeah, but you don't have to. I'm saying that usually, I would say you can use whatever linear transform you want.
Yeah.
And what I suggest using Fourier transform usually is better because
Yes.
you can randomly take those frequency components rather than randomly take pixels.
Right.
Because that's very risky.
Mhm.
You lose information for sure if you, once that you miss some pixel value, that's, you don't have that, then later
Right,
you
right,
cannot recover.
Right. The problem though, with using, we've all had this problem, is that Fourier transform
It's
is
not
nice.
acceptable.
It's nice as a matrix, but it's gigantic, you know? So we
So
can't.
that's why you cannot really write down this whole matrix A.
Right. You have to do it in a loop of some sort, right.
Implicitly specify
Right.
that.
And if you do it that way, CVX has a problem.
Yeah,
Right.
directly explain that.
Right.
That I didn't realize before.
No, I definitely agree. If you can use Fourier transform as your sensing matrix and full random, that's definitely better than anything that you've seen today so far. But this idea of doing A transpose B, or A inverse times B, that, I don't think that works. I think.
I tried doing that, and I tried slicing out the stuff that actually corresponded to what was actually taken from the original axis. And then CVX just basically, I don't know, about 15 iterations and then it died. It goes, oops, failure. So that didn't work for me either. Like, see what I took here? Okay. I took A transpose B, right?
Yeah.
But I didn't just necessarily compare it to X.
That gives you a vector the length of X, right?
Yeah, I sliced out the pieces that I wanted to.
How did you know which pieces you want? Because this Fourier transform, each element of the transform uses information from all of the pixels.
Yeah, that might have been.
So it doesn't quite work. I mean, if you do ATB, you will get some vector that has no zeros in it probably, and it's the same size as X.
Yes.
But X minus this vector, if you're trying to minimize this norm, or its constraint somehow, it's kind of determined already, because every element has a corresponding ATB element in it. But that's not what you want to be doing. You want to do AX minus B.
Well, but the
B
question
is lossy.
the X you get when you do that is in the Fourier domain. Am I correct?
No, X is in the image domain. A times X is in the Fourier domain.
Uh-huh.
Yeah.
Oh, I did try doing that earlier. I tried passing CVX to implicit function. It didn't like it.
Well, we've all had the problem that the A matrix, A times X, that
Yes.
Fourier operation doesn't work with CVX objects.
Yes.
And so that's been the problem at the moment facing.
And also, it's a bit surprising, I saw until some of you told me, and
Yeah.
I say you probably have to go into how the
Yeah.
CVI comparison is something like it doesn't really recognize this as a convex program. Then
Well, it recognizes it as a convex program. There's no problem with that. It's
Yeah,
just
but
when you
that-
try to compute Fourier transform of a CVX object,
Yeah.
MATLAB says I don't know how to do FFT of a CVX object.
Yeah.
That's the problem.
Yeah, that's the problem. And
Yeah.
that's because the CVX developer probably
Right. CVX, yeah,
didn't really recognize
It
as a
actually
convex program.
overloaded a lot of the functions. Like norm, there's a function norm that the CVX people implemented
Yeah.
that operates the same as the MATLAB norm, but it works on CVX objects.
Yeah.
So any function that we use that works on a CVX object, they had to write on their own,
Yeah.
like redefine it, especially for this case.
There's a very nice norms flow.
Yeah.
That they wrote with Firstall and MATLAB vectors as well as their own.
Yeah. Norms is clever. I didn't know about norms. If I know, I would have changed my formulation.
Yeah.
Yeah.
I was messing around with Octave and they have a vectorized version, just the right one.
Okay,
But
so
anyway.
I guess that's pretty much about the assessment project, right? Then the remaining part will be under some very new things. Okay, so first, thanks, Dan.
Oh, come on.
Okay,
Oh, no, don't format. Oh, good. Ah, stupid.
Can we take a quick break? Maybe?
yeah,
Change
so
your
let's
topic?
take
Okay.
like 5 minutes break.
Yeah.
Where is the USB drive? Where is the USB drive? Nah.
Oh, look, you take the sensing matrix A, right? This is the discussion is on the matrix A. The way the code is sampled and often represented is you take your image X, you unload it with X, right? You take the Fourier transform from this vector, okay?
Where is the
You
USB?
get another vector of the same length, right? Fourier
Here?
transform, right? And then you randomly sample from the Fourier transform, right? So you have to use every element of the
Oh, where is it?
Fourier transform uses information from every pixel in the original domain. Right. And so this A matrix is dense.
Yeah,
If it
and
hadn't been
that's
dense-
important.
Yes. So
It
we
doesn't
had
recognize?
problems using
Yeah.
dense matrices.
Recognize.
So you make a Fourier transform
Where is it?
of that column X.
Yeah.
And ready to use?
And,
Yeah, it's here.
then what?
No.
Then you randomly sample from the Fourier transform.
That means times the matrix A.
No, A times X. Well, let's say A1 times X is the Fourier thing, right?
I want to
And
remove
then
this one.
A2
Yeah, I
times
want to
A1
put it
times
somewhere
X
now. I just want to change
is some of the components of the Fourier thing, right? So in this case, your sensing matrix will be A2 times A1, right? Right, but this matrix will definitely be dense. So if you have an original image that's 65,000, you want to reduce half the number of elements in it?
The operation is not steep.
Right.
I feel like
Yeah.
you have to have some physical device to
Yeah.
really achieve that.
Yeah, yeah. Well, if we could do it algorithmically,
Yeah.
which, like fast Fourier transform is a very, very elegant
Yeah,
algorithm.
so what I'm saying
Yeah.
is, if you really want to build like hardware device,
Oh,
you
yeah,
got,
yeah.
you got to, for instance, have the FPGA board. to
Yes,
build
to do
it.
the fast Fourier transform. Yeah, definitely. And sampling at the same time. Right. Right. We're having MATLAB issues. We haven't planned enough as far as.
Yeah, and also I didn't expect that. Originally, I just tested with second core program in MATLAB. I thought it
Oh,
was
yeah.
doable, so.
Yeah.
So I guess CVX could do better, but like, and then it's very surprising to me because you guys run like real half an hour to
Yeah.
finish the first.
Yeah. CVX is, even if you have like a little like 5x5 image, CVX is not instantaneous.
Yeah,
It's
well,
still-
it takes some overhead.
Yeah.
No, because it's educational version, it's not really fully optimized. so-
Yeah, well, I didn't expect it to be, yeah.
It takes a while just to build the program.
Yeah.
That's what a lot of the overhead seems to be. Once it actually runs it, it runs quick.
Like on the 512 by 512 that I did, it took almost an hour to finish,
Yeah,
yeah.
it's very surprising because I think
It's a
it
huge
takes
image.
me a few minutes
Yeah,
to run the actual like sort of second core program.
and it works.
Well, you saw the.
So that was your vote, so that's what how you got yours. Okay.
Basically, that's what I expect.
Yeah, MATLAB built it.
And that-
The MATLAB function that did that.
No, I think I gave part of the code to Sai. So if you want, you can ask him about, for instance, using that part of the actual optimization routine. That's something you can really understand. I think it takes time and effort to understand about the technical program, but that's basically the way it works. And also, I think I put in like a Newton method to at least try to approximate this action.
Right.
And sometimes it works better, but you know, it takes risk.
Right.
So current program, you feel probably it's worth the effort to make education.
Mm.
Okay. because it's data, more data collection probably is better than some naive approach.
But this, oddly enough, because it didn't work with that function, we had to give some thought to the sensing matrix.
Yeah, that's good.
So
because
it kind of,
yeah,
it's good in the long run.
yeah. I mean, it's good to explore
Yeah.
how this idea works.
Yeah.
Like propose, maybe back objective function.
Yeah. Just like what?
Okay. You see any connection to compare something?
Yeah, that's the A.
Yeah.
Yeah.
Okay.
Yeah, that's why we have a discussion. That's why we call it the sensing matrix. I know what you mean. Can I have one of these comments? This is for extra on presentation. We'd be done that. Jointly.
Okay, if you, just let me see. Yeah, it's like this. Which button? This is the first button. Yeah. And this one, then you can just open it. You can just make it full screen.
Change slides and swap roles. A little that.
I think it's better to use speak for.
I think I also speak very loud, so it's fine.
You don't have to listen to make yourself comfortable.
Should I just do it like this? I don't know. I don't want to do that. I don't want to do that. Give me in my hand. Oh, can I roll with this? Yeah, I can.
So this is, but is this, because I use the Acrobat Reader.
Oh, otherwise, what can I do?
I don't know, does mine do that too, or no?
No.
Okay, so this is a PowerPoint.
Because this is, I think this is smart for.
No, but I will see you.
So PowerPoint,
No, I will go there. Oh, okay. I don't want to wait. No.
No.
Put it in your hand. Yeah, I can put it in my hand. Wait, I wanted to keep my dress very well. But you should see
Yeah,
the
no,
back.
every time it's a problem where directly go to page 17.
You want we both will stand here? Is it okay? Yeah.
Put in
Yeah, yeah. Otherwise, you will also come with you.
Right,
Wherever I go, you'll come with me.
right.
Sorry. Oh, it's getting recorded, so we should not laugh.
No.
It's getting recorded.
It's all.
Right. But I think
And where to change the slides?
Yeah, it's better.
Use this. Which one?
Mine
Wait,
looks,
can we change the slides?
Oh,
no. You need to push back.
you can do that with Gamer. You can definitely do that with Gamer.
Okay, over there. Where? Yeah. But how can we change the slides? I think we cannot.
Surprisingly good.
Every time we need to go here?
Yeah.
Oh.
Okay.
I liked it.
But you think it takes effort also to show like a graphical model and the metric market algorithm.
Gurung, we are missing you.
We
are missing you.
Come here. Text is not easy. So drawing a picture by hand is good.
Gurung
But,
is
you
missing
can
you.
definitely draw like a couple of pieces and then uncover them one at a time in Gamer. That should be easy.
Yeah, but the control of the overlay.
I don't think it's hard. I haven't tried. I don't like the overlay stuff. I don't think it's hard.
Well, it takes time because I think
You've tried it before. Yeah.
well, I tried before, I don't like the existing packages, but if you want me to really pick the right tool to do that, it's you have.
Okay.
So we will try it, but I think probably we want to get started.
Okay.
Okay, thanks, and we have like a joint effort by VP and NAN for a very interesting topic called it's called iterative grading algorithms for reconstruct gene regulatory networks.
Yeah.
So I think for people unfamiliar with the background, maybe need to take some effort to
Sure.
introduce about
Yes,
the problem.
Sure. So, hello everybody. Hi. The title of our class project is Iterative Greedy Algorithms to Reconstruct Gene Regulatory Networks. And as Dr. Chen said, I and Nan have worked together on this class project. The main reason why we chose this topic was to make use of some of the techniques which Dr. Chen discussed in the class in our own research project. And as Dr. Chen knows that one of our ongoing projects is on network reconstruction. And I particularly liked greedy algorithms, which he taught in the class. So I discussed with him, and then we came up with, I and Nan designed some algorithms to construct these gene regulatory networks. And we are also proposing some of the extensions of these algorithms. So here is an outline of our presentation. We will first go through the background of our problem, followed by the problem statement in terms of optimization function, objective function, and then we present our iterative greedy algorithms and with some possible extensions, and then finally Nan will present the simulation results. Oh, there's some. I think there's some problem with the PowerPoint here. So anyway, in the field of bioinformatics, we have a large amount of high-dimensional data which is available for us to analyze. Okay, and these data sets are often obtained as outputs of very complex biological systems, which can be viewed as networks. Okay, and these networks are often driven by hidden regulatory signals, which of course are hidden, so we cannot observe them. Okay, and it is one of the very challenging problems to reconstruct these hidden regulatory signals as well as the underlying network topology. And what do we mean by the underlying network topology is nothing but those connections between the hidden nodes and the output nodes. Output signals are nothing but the signals corresponding to output nodes which we observe. But looking at the data, we want to reconstruct these hidden regulatory signals and various connections between hidden nodes and the output nodes. And some of the traditional approaches which address this problem are principal component analysis, independent component analysis, and network component analysis. They all have got their merits and demerits. For example, principal component analysis and independent component analysis, they actually ignore the underlying network structure and assume various statistical constraints on the computed hidden regulatory signals. For example, principal component analysis assumes them to be statistically, it assumes them to be orthogonal, and independent component analysis assumes them to be statistically independent. But this may not be the case with the real world data sets, and therefore these two approaches lack biological foundation. Okay? NCA, on the other hand, does assume a prior knowledge on the underlying network topology, but then there are several issues associated with the uniqueness of the solution. For example, we are only guaranteed to get a unique solution up to a scaling factor under some identifiability criterion. Okay? And here we can explain the situation in a better way. For example, in this diagram, we have 6 output nodes, and correspondingly we have 6 output signals. Okay, this is what we observe. And we have 3 regulatory nodes, and correspondingly we have 3 hidden regulatory signals which we do not observe. But these nodes regulate these 6 nodes, and so correspondingly we have various connections here. And these values here, on these edges, they represent various connectivity strengths. Okay? So from these data sets, for example, PCA, the underlying assumption in case of PCA is that these signals are orthogonal. And in case of ICA, these signals are assumed to be statistically independent. And NCA assumes the presence or the prior knowledge on the presence or absence of these edges. We, on the other hand, in this project, we do not assume any of these things, but what we assume is that these hidden signals belong to a dictionary, which is available to us a priori. And this dictionary is overcomplete. That is, it contains many elements, and we want to select the best signals which represent our data. We need to select them one by one, and this is how we are going to make use of greedy algorithms to make selections in a greedy way and to reconstruct these hidden regulatory signals. And once we have the solution of, now let me explain a little bit. Can I go back and just look at this? Sorry. Yeah. So this kind of problem actually results, in a broad sense, it results in a matrix factorization problem where we have, say, m signals, so which can be represented, this is an n by m matrix, and then we have a phi matrix of So this kind of problem can be actually formulated as a matrix factorization problem, where we are given m different signals, each of length n. Each corresponds to a measurement of length n. We have n different measurements corresponding to each signal. We have m different signals, and we want to find its low dimensional representation, where we want to construct this matrix phi. Phi contains these hidden regulatory signals, and A contains those, this matrix A contains those connectivity strands here. Okay? And in general, this matrix A is going to be a sparse matrix because these biological networks are in general very sparse. Okay? So A is assumed to be a sparse matrix, phi, which contains this low dimensional signals, and what we are given is actually this matrix Y. Okay? So, but then this problem can further be restated as finding the solution of this kind of problem, that corresponding to each of those signals, we have to find this matrix phi and a sparse vector ai for each I varying from 1 to m. So in particular, this problem reduces to finding the solution of given one signal and reconstruct these hidden signals and a sparse vector ai. So we have actually first considered this simplified version of the problem, and then we will propose how we can extend it to the case of multiple signals. Okay?
So now what is available to us is our observation.
Yi, yes.
Y.
Y, yes.
So that means you even don't know you regulatory nodes and those connections.
We don't know, but what we do know is that those hidden signals, they come from a dictionary which is available to us. But we need to select the signals from that dictionary. A dictionary I will define. A dictionary contains many signals, S1, say S2, S1, S2, and it may be say a countable set. But we don't know which of these signals actually correspond to these hidden signals. But we do know that our hidden signals belong to this dictionary. But we need to select the best signals from them from this dictionary to which best fit our data.
This dictionary means the candidate set.
Yeah, kind of candidate set. It's overcomplete because there may be many candidates corresponding to one given one signal. There can be many candidates which may represent our data the best. But we need to make selection in a greedy way. So, and once we have the solution of this kind of problem, I am particularly interested in one of my research topics, which is on dimension reduction approach. And if this is going to be really helpful for me in this of my research topics, where I assume that a large network, because in bioinformatics we often there is a very big problem. Most of the problems suffer due to the high dimension of the data. Because in general we have a large set of genes in a data set, and so we are looking for we are actually developing a dimension reduction approach to deal with this kind of problems, where we have a large set of genes and many existing algorithms cannot accommodate so many number of genes. So once our underlying assumption is that a large network is composed of many small overlapping networks. A small network can be decomposed into small overlapping networks. And once we have the solution of these kind of problems, that is, we have a phi, we have computed our phi, and we have computed all our AIs, then these AIs, which correspond to this matrix A, each row of A, that is, we have L different rows in A, they will correspond to one subnetwork. And once I have those L subnetworks, I can combine them to form a single network. Which is not the network which we just saw. This is a network between genes to genes. So this is one of the ongoing projects, and hopefully this solution of this problem will also be helping in solution of this problem. Sorry. So here we formally state our problem, optimization problem. So we are given a vector or a signal of length n. Length n means we have n different samples, and it corresponds to just single gene. And we want to estimate a matrix phi of those hidden signals, that is this matrix phi, and a sparse vector A, such that this norm is minimized. And our underlying assumption is that our hidden signals belong to an overcomplete dictionary which is available to us beforehand. Okay. And here is our first algorithm, which is a greedy algorithm, and it is iterative in nature. So our initial approximation to our signal is 0. The residue is the signal y, and our basis collection is empty. Initially, we have no elements in the basis. Basis means this matrix phi here. Okay. Initially, we have no elements. So in the first step, we first select one element of the dictionary in a greedy way and put that in our basis. But how to make selections? This is the same. It is the same way what we learned in Dr. Chan's class for matching pursuit, and it is one of the standard ways to select elements in a greedy way. And why this criteria? Why we need to select one element of D which maximizes this inner product is that these elements G will form. We are looking for those elements which actually represent the basis. Okay, that is, every signal can be represented as a linear combination of these elements G, right? That is, we are looking for, suppose we are given a signal Y, we want to find those GIs which can be represented as a linear combination of the basis elements, finitely many of them. But this is an approximation, so we do have one residue. So our next element will be the one which will maximize the inner product, which is the closest to this residue. That's why we have this criteria here. Okay, so in the first step, we make a greedy selection and introduce a new element in our basis. Now, as soon as we have our basis, we define that as our current phi. Okay, and once we have our phi matrix, then we can solve this least square problem with L1 penalty, because we need our A matrix to be A vector to be sparse. And from this we have solved using CVX. Which solve this in this few lines of codes. And now once we have our phi matrix and once we have estimated our A matrix, we know what is our next approximation to our signal. This is just phi A, and then we have the residue, and then we have the error. And then we repeat this process iteratively until it converges, or our error becomes below a cutoff. Any questions so far? And we have, as Nan will be presenting the simulation results, you can see that error is monotonically decreasing, and it becomes sufficiently small after some time. And here is another way, another algorithms that we design. The initialization is the same as before, and even the first step is the same. Every time we make a greedy selection and put the new element in the basis. But as soon as we have a new element in the basis, we remove that element from the basis which causes the maximum reduction in the error. That is, we check it exhaustively and remove that one element from the basis which causes in the maximum reduction of the error. And then we update our basis and define that as our phi, and then again we solve the L1 regularization problem. And then again we define our next estimation of next approximation to our signal and our residue and the error. And again we repeat this procedure iteratively until it becomes less, the error becomes less than a small number.
So what's the difference between this algorithm and the previous one?
In this case, it is stepwise. In each case, we also remove, as soon as we add, we also remove one element, if at all it exists, which reduces the error, overall error, this error.
Which one you like it better?
I like the first one better because this is more time consuming, and the data set which we use, there was not lot of difference, although it takes the number of elements in the basis for this case is less. But I like the first one because it is faster, and moreover the results were quite comparable with this one. But I think Nan liked the second one. She liked the second one.
Or any particular reason?
No, I'm not saying I'm like the second one is exactly close to the true Y. Then
You mean it approximates the observation diameter in terms of minimizing the actual residual that you observe?
yeah, but
Yeah,
it's just a little bit.
Little bit.
And also sometimes the basis, number of bases choose into the phi matrix is smaller than the algorithm one. But it's hardly happen.
Hardly-
It's,
hardly-
most of case is the same with this.
Most of the cases
Yeah,
are the same.
but I think
They chose identical subset of the basis.
Exactly, yeah. For the field,
yeah.
yes.
But
Sometimes there is no difference, so they just choose the identical set of elements. But in some cases, for some data sets, yes, there is some difference.
yeah, it's highly depend on the data
The
sets.
data and our dictionary, mainly our dictionary. How correlated?
Of course, you all start from the same dictionary.
Yeah.
Yeah,
Yes.
yeah.
Presumably.
Yeah.
And then I think if the difference is maybe from like the representation of the data.
Right.
So it's over complete basis.
Yeah.
then, of course,
Sometimes if the data in the dictionary, one column, one vector, one signal is less correlation, it will cause.
Okay, so if it has less correlation.
Then we get much better results. When the dictionary
Yeah,
elements,
of course,
yeah.
you can always measure the so-called incoherence of your dictionary. And that's a very strong indicator of how well you take your dictionary.
Dictionary, yes, yes.
Here we have a penalty of the sparsity.
Yeah, penalty. Oh, in this case, we have fixed it to 0.01. However, because in this case, we were not particularly interested in estimating lambda, but we wanted to see the various trends in the results. And in various simulations, we fixed this lambda to a fixed value, and then we observed the trends were the same. But in general, this parameter lambda can be tuned. You can yeah. You try different values of lambda, and then you just get the best one.
Well, in general, there's so-called regularization parts, meaning that, for instance, you make lambda maybe from small value to large value, you see how the sparsity changes.
Changes, yes.
And that in statistics, like a
Lasso, yes.
standard way to
See, yes.
all the possible regularization.
Yeah, but in our case, we actually fixed it to a value 0.01.
I mean, if lambda get larger and larger, probably your solution gets
Sparser and sparser,
but your
yes.
residual time.
Yeah, residue will be larger.
Is
A
there
trade-off.
guideline
Yeah,
or
trade-off.
No,
No.
I don't think so. It's application dependent.
Yeah.
Okay, okay.
Something like if you have some tree expression data, you want to know how many scale signals are there, you need to know roughly how much residual to expect.
Right.
Your A, when you say sparsity, right now you're also giving weights to, like you have which nodes are connected, so which edges are present, and also the magnitudes, as opposed to just how many edges are present. So I thought sparsity was just how many edges are there.
Oh,
And also the
magnitude.
Magnitude.
You need to estimate. If you say, for instance, the signal 1, 3, 5
Yeah.
are the hidden regulation signals, then you also need to know how much.
How
It's
much?
not trivial to the expression.
You certainly need to get an estimate of the weights of the edges. Right, I agree.
Yeah.
But when you're penalizing for sparsity,
Mhm.
it seems that if you have 3 edges there, then the sparsity should be 3, not the sum of these.
Oh no. In our case, what we mean by sparsity is the total the locations which correspond which become
like
less than this
non-zero
divided by
Yeah, the number of
Yeah.
non-zero entries.
Hey,
Yes.
Right. but
Number of-
Isn't this the kind of like a sum of the weights?
but-
but this L1 penalty implicitly regulates.
Regular. Yes. L1. This implicitly it means the same thing. When L1 becomes you see it this way, when L1 norm of a vector is nothing but sum of the absolute values. When it goes to become smaller, it means magnitude of those elements have to go smaller.
Right.
So
It's I think it's a relaxed version of so-called L0, which just comes directly.
Directly, yes.
How many non-zeros? you
Right.
reveal.
Well, I was
But that's combinatorial, so that's proved to be anti-hack, so people try to at least find some approximation to that.
yeah.
And L1 is amenable because it's like linear constraint for penalty.
Yeah, and as Nan will present later, when we have considered the sparsity, we have considered those locations which become sufficient. We put a cutoff and then we count those entries, count the number of those elements which become less than that cutoff, and we divide by the total number of entries to get the proportion of the sparse locations. So this is what we have considered.
So you do this
Iteratively, yes.
So your termination criteria is that get a
Dep-
value of the
Yes, but it depends on the data what cutoff of the error you want to see. Sometimes if once you fix point, say 10 to the power minus 6, your data never becomes less than that. So you have to put a cutoff.
You got to know,
No, got to know
roughly
the residue value.
So your termination criteria is the residual level.
It's the error.
Yes, the error. This one becomes less than a sufficient small number which we fix. And the third algorithm is the same as the second algorithm, with the only difference that now we do not have any greedy criteria, but we select an element from the dictionary in a random way. And it was assumed that it will perform the worst, which it does among these three.
Well, you don't need to test that.
Yeah.
Because if you just randomly pick a candidate and hope it will do the job. Yeah.
No. But once we select it randomly, at the same time, we also remove that element from that dictionary, which reduces the error the most. So we again do the same thing, but in the first step, the selection is random. But at the second stage, we again remove that element which reduces the error the most.
Yeah, but the first stage can be disastrous.
Yeah,
If you
the
pick
first
the
stage.
wrong candidate,
But
Yeah,
but
but
it
in
is
the
most
second
likely that
step-
it will be gone in the second step. It is also the possibility that it will be gone when we
what's
make.
the motivation of doing this?
Doing this just to test whether the greedy way or the random way, because when I was discussing with you on NCA and you said that you don't like NCA because it makes random selection, because
I probably didn't.
no, there was but random, because I was very much interested initially not to use the greedy algorithm but to make an iterative algorithm by random selection, but then so I didn't. That's why that was the main motivation why I wanted to check this. Okay, so now the next, actually this extension which you are proposing, I'm not sure how good it is, but I want to certainly tell you why we want to do this. For example, just now we saw that whenever we are given a signal, yi, we have correspondingly we can reconstruct a matrix phi and a vector yi, ai, right, sparse vector. But for different signals yi, we get different phi's and different ai's given a signal yi. Okay, but in that dimension reduction approach, I want to reconstruct a matrix phi which remains the same for all yi's. Okay, and so for that reason, that was the main motivation behind thinking about this algorithm, where at each stage, in the first stage, we select that element from the dictionary, which on an average maximizes this inner product.
Yeah, that makes sense.
Yeah.
For instance, you can say on average just directly to the inner product, but that's equivalent saying that I want the overall residue.
Yeah. Yes. That's why we define, in the first stage we define this function, and then in the second stage we select that element which maximizes this average value. So it is like orthogonal to all of the more closer to all of the residues on an average. And then once we select this element, we again put it in the basis, and then we define our phi to be this basis, and we solve these m different L1 regularization problem. And then we have solution of these different AIs. Then we can construct the approximations to our original signals and these residues. And now we defined our error to be the sum of those L2 norms. And then we repeat this procedure iteratively. The solution of this will give me a solution of this kind of problem, yi is equal to phi ai, where phi is fixed for all of them. And then that it will be useful for my research, that once I have these sparse vector ai, then I have many zeros in this matrix A, and then I can look at forming those subnetworks and then form the whole network. Yeah. So this part was for the multiple genes, and I think now we have some results, which I think Nan will be presenting. Yeah, Nan will present the results.
Okay.
Don't need that. Okay.
First is the simulation study for the running time for these three different algorithms. And we first test one signal, which means the y is 1. one vector, which is one gene signal inside of a matrix, and then
explain a little bit about, for instance, the length or the
oh
size
yeah,
of the
the length is n here is equal to 20, and it's one vector. Then the phi matrix is definitely the basis length is also equal to 20, and the L is the column number is equal to 10, and then we got A matrix is still a vector which is
10 by 1.
10
10 by 1.
10 by 1. Right? Yeah. And in the dictionary, we have 20 bases.
200. Sorry.
200, sorry. 200 bases as a candidate.
Okay.
Yeah. And for each time we generate Y data, then add some noise in there, then we run our code to for these three algorithms. Then we run 100 times and calculate average running time for each one. And we can see for the greedy one, it is very not time consuming. It's very fast. Usually is around 1 second or something. And for the second one, since it's back and forth, so it will take about 4 or 5 times of the first algorithm running time. But for the random-wise algorithm, it's take very long time. Then, so most of us don't like this way. It's not and just for testing. Then this one will save you time. But this one, the time is still time management, but maybe it's because this number is still very low. If this is very high, so the time will be another issue.
Yeah.
So you mean, for instance, if my dictionary is 2000,
Yeah. Yeah.
200, then you expect that this greedy stepwise will be
Will
more time consuming
yes,
than the greedy.
yes,
Yeah.
yes, yes, yes,
Yeah.
definitely. Although it may contain less number of elements in the basis.
Okay, so which one is actually better in terms of, for instance, close to the ground truth that you generate?
The second one, of course, the greedy stepwise.
Okay.
Yeah. You can just.
This one is the final. Actually, the arrow is on the vertical axis, and the number of elements is in the
It's one iteration.
horizontal axis. We can see the number 1, 2, 3, 4, 5 is the first element into our feed for the 3 different type of algorithms. This is a special case because as I said before, it's very hard way to find a case that a greedy algorithm and greedy stepwise have some difference, but this is a special case. I just want to show sometimes it has some difference. You can see from the first one, this one, the algorithm one, a greedy algorithm and a greedy stepwise is the same until the first 6 elements into our feed.
On your horizontal line, the x-axis number of elements in the basis, when it's 1 that has larger error, which indicates like
This one is left arrow.
error means residue.
Yeah, yeah.
Yes,
That just means, of course, if I only choose
one element. Yes,
Then
we cannot.
then
corresponding error
corresponding
is
error is large.
Large,
But
yes.
the basis that I chose, is it really correct or not? Do
Uh,
you have any clue on that?
Actually, we did observe we did compare after our algorithm stopped. We compared the true phi with what we computed, and we did observe some of the basis elements are exactly present there. But since in our data set the dictionary signals are very much correlated, so sometimes it selects some other elements which are very close. Highly correlated. So for that, to verify that, what we computed is we computed the correlation, Pearson's correlation between the signals, what we computed and this, and we found very high correlation. So that's why we thought it's fine. Yeah.
Yeah, and the overall trend, definitely the arrow is
Yeah, but when you show this, do you know, for instance, that this greedy and greedy stepwise chose the same basis based on the same data?
Oh no, you can see that up to stage 6, when they add elements up to.
If the error are the same, doesn't mean they chose the same basis.
No, they chose the same.
Yeah,
They chose the
this
same.
one
With
is the same.
same that we observed.
Exactly the same.
Exactly the same.
Okay.
Yeah.
So,
Yeah.
so the highlighted they are the same.
If two bases are highly correlated, you never know.
You never know. Yeah. But in real.
But since the error is exactly the same.
Okay.
Yeah.
And also we checked for the first
Okay, I see.
one is the same.
Yeah.
Yeah. And here the cutoff for the error is 0.2. So these three all stop around here.
Yeah.
Around here. But you can see for the
Greedy.
greedy algorithm is one more basis include and the greedy slide by accessor stop at 7 bases.
I'll go to the next slide.
One of the strange for me is that you random stepwise from 3, from basis number from 3 to 5, even increase
Not the increase, it's just
Flat.
Flat.
yeah, flat.
from this.
Yeah.
Sorry.
So which means when we add another new element, it
Doesn't
cannot reduce the
error.
error, but it cannot increase error.
an error.
You shouldn't add that, but anyway.
So the newly added element of basis is redundant.
Yeah,
Yeah,
it's
that's
kind
why.
of, redundant,
Redundant.
yeah.
Yes.
At least it cannot reduce the error.
Yeah.
Is this actually the number of elements on the x-axis, or is it the iteration number?
Iteration and the number of elements in the basis actually coincide.
Yeah,
They are the
No,
same,
but-
right?
but Like for this random step size, the flat part means you added a vector and you removed the same vector.
We added one element. No, not the same vector. We
But the
removed
error
that
is
element.
not changing.
Yeah, because suppose there are no elements which reduce the error, it will remain the
Yeah.
same.
Yeah.
Because it will remove an element only when it reduces error. Suppose it cannot find any element which reduces error, it will remain the same.
Oh.
Yeah.
So you added 3 elements without removing any, and
Yeah.
the error did not decrease?
Yeah, it did not decrease. It depends on the dictionary, right? How many, how it chooses the elements in the dictionary.
Having absolutely no reduction, I kind of find that hard to believe.
Probably because in a dictionary we observe that their signals are highly correlated. So.
Or my thinking was that if you add a vector
Mhm.
and you remove the same vector, obviously the error has not changed.
Mhm.
So I was wondering if this x-axis is actually iteration number and not model size. Is that what?
It is iteration number, but it is iteration number because in every iteration we assume that it adds one element.
Yes.
It adds one element, right?
But
So-
so if you add one element,
Mhm.
the error should decrease
Yeah.
marginally.
But I tend to agree with that,
Yeah.
but still, I think eventually this random stepwise will not be the
Yeah.
choice.
Yeah.
Yeah, of
Yeah,
course,
yeah,
it is not.
Future consideration.
Yes.
Yeah.
But still, the implementation may have some minor issues. I think.
With the random ones? Okay. Or maybe we need to write instead of number of elements, the basis number of the iteration number. That would make more sense, right?
Iteration.
Because number of elements in the basis does not change. This is what Rustin means. So we probably need to write number of iterations in place of number of elements in the basis.
Another indication is whether you take wrong basis or some basis should be there but you didn't.
Okay.
And these are like two type of errors.
Yeah.
in this.
But I don't think that's a problem. I think we just need to write here the number of it is an iteration number because in some iterations it may not remove an element. It may not
What I'm
remove.
saying is by just saying, okay, I can reduce the residual
Mhm.
from my dictionary, but that may not be the true basis from originally that you actually generate your observation.
Okay.
And that's important because later when you study gene networks,
Mhm.
if you take the wrong regulator, then
Mhm.
the whole explanation can be completely
Yeah.
incorrect.
Yeah.
So probably it's better to indicate two types of errors. One is like if you take the wrong basis. The other is some basis should be picked, but you didn't.
Didn't pick. Okay. Okay. Shall we go to the next slide?
This one is the error and the space trade-off figure for the first greedy algorithm. For here, we set up a different error cutoff. Then for here is the sparsity, which means the density of 0 in the A matrix, which we set a cutoff like 0.1. So every entry in the A matrix is below this number is treated as a 0.
Well, what's the ground truth, you know? Like the true sparsity of A when you generate.
We know.
Yeah, but what is it?
What is it?
Sparsity is,
Yeah, like you change the sparsity to generate this curve, or you have a fixed sparsity,
we have a
Fixed.
fixed sparsity,
which is
which is point,
Which is use
I forgot.
Gamma or
no,
gamma.
not that one. The
I mean, the
sparsity.
actual value.
Oh, the
I think it is 0.7, something, 0.7 or something, 0.7.
If it's 0.7, then this range doesn't really look right. Because
0.7.
there's no hope you can actually pursue for sparsity below 0.66. If the actual sparsity is 0.7.
0.7.
No, the actual sparsity.
The actual sparsity has to be within this range, like from 0.52 to 0.66, if you want to show some error versus sparsity trade-off.
Actually, we just wanted to, here in this case, irrespective of the truth, we wanted to see the trend.
And
That when,
also, how much noise did you add to this?
very
Like the
small, very
the
small,
residual.
very small
then-
noise.
Like, do you expect the error to be 0.1 or 0.2 or 0.05?
We just added a small error to that, noise to that, and we just fixed different cutoffs to see that if our algorithm stops before,
Well, I
then what is
hope
this?
that, like, at least in your report, you need to document how you generate this kind of error versus sparsity.
Okay.
without
Yeah, sure.
simulation side.
Mhm. What happened? What happened?
No, I think they
What
changed
hap-
it from next floor.
So what?
I don't know how to. And similar is the train for.
Yeah, so the simulation for this figure is we want to see the trend for the error cutoff. It's showing when the error cutoff is larger than the sparsity is lower, which means you can tolerance more, much more error than the number of zero in A matrix to be
Small.
the density of the zero entries to be
Small.
small.
Yeah, of course, that's intuitively right.
Yeah,
but
but-
still, for instance, the key question is under certain sparsity and under certain noise level that you probably know, is it possible to recover such an unknown hidden
Yes.
network?
Sure. That we need to think about it.
Yeah,
more
something like,
carefully.
for instance, if noise level is on 1, you definitely know no matter what sparsity level you generate, there's a hope I can find the cutoff and identify the correct basis.
Right.
Otherwise, you don't know.
Yes. Shall we go to the next one now?
Okay.
This one did not change the sparsity much.
No, this is
the random one.
the random stepwise, so it's for some cutoff it's not changing much. It's like a
The
flat.
sparsity does not change.
Yeah, because even though the entry and location in the A matrix have some change, but the density is not changed.
Yeah.
And this one is the extension version for the y is equal to a matrix and A also equal to the matrix. Then we set the number of iterations as 50.
We just wanted to see the trend and the
Yeah,
error,
so
how
this
it
is just for the greedy algorithm, because for the matrix calculation, if we do the second algorithm, it will take a long time, so we just test the first algorithm.
Okay, but how many signals do you
Oh,
do you observe?
For
In
M,
this one,
M
40.
here
40. I
is
think.
40.
Okay. And this error corresponds to
The sum of the error.
the
Some of the residue.
Yeah.
Yes, some of the
And
residues.
in your simulation, like what do you expect? Like when you generate the data, like what's the actual residual level?
Actually, residue level.
We just want to test if our algorithm work for the matrix version or.
Yeah, I think it should work.
But we didn't
for
know if it
instance,
would
your
work.
actual residual level is from 1 or from 0, 1?
we didn't compare
Well,
with the,
we didn't
compare.
use the error
Yeah.
as the stop criteria because
In this case, we use the number of
yeah,
iterations.
because we don't know what the level is the correct level. Otherwise,
Well,
it
of
will.
course, let's say the actual error level should be 0.1.
Mhm.
You can still go below. If
Below.
You chose
More
bases.
bases.
So then you're overexpressed.
Overexpressed. Exactly. Yes.
From this figure, we can see from this point is kind of black, so maybe we can use the cutoff as 0.0 something. Yeah?
Well, that's not reliable. If you don't know what residual level you expect to achieve.
No, in this case, we have just wanted to see the nature of the error when we increase the number of iterations.
Okay.
That was our main purpose. We didn't want to compare with the original residue or something.
Yeah,
So
but
this,
that's important.
yeah, that we can take care of in our report. But this was the main purpose, that we wanted to show that our algorithm for the multiple signals does work.
Okay.
Yeah. And then in this case, we also show the trade-off.
In the matrix version, we also show the error and the sparsity trend is also decreasing monitoring.
Yeah.
Okay.
I think this is all.
Yeah, this is all for our results.
I don't know why it is going out of box. Okay, so these are the references that we used.
We should mention some
Pitfalls?
some problem of dictionary.
Yeah. That's a question with Dr. Chen. Dr. Chen, we have just one question. No, for example, in real data sets, we don't know which dictionary should we choose. So how to go for it?
I'm sorry.
In case of real data sets, for example, these were simulation studies and where we knew from where our hidden signals come from.
Okay.
But in real data sets, when we deal with real genetic data, we don't know which dictionary to deal with because we don't have any availability of.
Well, you need to have some prior knowledge to begin with. Because, for instance, otherwise I can have a million different ways to explain. For
Yeah.
instance, let's say I have one sinusoid.
Yeah.
Usually I know that this is a pure sinusoid.
Mhm.
Right? And if you say I have some bizarre signal,
Mhm.
it can have many different harmonics.
Mhm.
And this harmonics is considered your dictionary, for instance. But if you say to begin with, I could also use non-harmonics and use zigzag waveforms.
Right.
And that's my dictionary.
Mhm.
Because I have no clue,
Mhm.
then you have a million ways to explain the signal.
Signal. Okay.
Right? So that's why, because I don't know your recent area, I cannot make specific suggestion. But I would believe that if you study certain small size gene network, you
Mhm.
probably know some hidden regulatory signals.
I see. And we need to think about it. I don't know that we.
I believe so, but I think overall, of course, I focus on the optimization
Yeah.
part.
Yeah.
and it seems fine.
Okay.
Okay, thank you very much.
Yeah, we can do it. Nan, where is my pen drive? Oh, it's there.
So even though you use that even software designer, you still for that problem.
Okay, my project topic is solving voltage assignment problem in embedded system use dynamic programming. This is outline. First, introduction and a simple example, and introduce the model and dynamic programming. In many embedded systems, some tasks contain conditional instructions that have different execution times for different inputs. Due to the uncertainties in execution time of these tasks, my project models each varied execution time as a probabilistic random variable. The objective is to minimize the expected value of total energy consumption while satisfying the timing constraint with a guaranteed confidence probability for embedded system. And
People know it has your hyperspace probability.
Okay, random variable, yes. And now I give a simple example of this. There is a job include 2 sequential tasks. Here we in load 1 and load 2. Each load can select one of the 2 different voltages, V1 and V2. The execution time T corresponding probabilities P and the energy consumption of each load and different voltages are known from the table. This is the execution time T of each node is modeled as a random variable. For instance, node 2 can choose one of the 2 voltages, V1 and V2. When choose V1, node 2 will be finished in 1 time unit with probability 0.3, and will be finished in 3 time units with probability 0.7. The problem is, given the minimum expected total energy consumption, E, and the confidence probability, P, and the timing constraint, L, we need to find the voltages for each node.
You have a voltage V1, V2, but for
Yeah.
example, if you know the 2, you choose the voltage 1, you have probability 0.3 to finish the node in 1 second, and 0.7 in 3 seconds.
Yeah.
But these 2 pieces consume the same energy.
Yes, the energy is, the consume is on the voltage 1. The energy, yes, depend on the.
I would assume the energy is over over a time span. Maybe you can take the average. Otherwise, it doesn't make sense. For instance, you say this time in 1 second I finish the job. The other time maybe the execution time takes longer. Usually you consume more energy to complete that. I feel this energy.
Yes.
Because I feel
This.
three probably on average I need to consume that.
Okay. This energy is depend on the voltage. Yes. Yes.
Well, I don't know because underlying embedded system probably depending on the actual instruction and the actual task you assign to that to the execution.
Not the energy is depend on the voltage. In this voltage list, energy will be this.
So this V2 is supposed to be lower than V1, right?
Yes.
Because
Then he needed to move on to.
lower energy, that means you use lower voltage to operate on the embedded system.
Yes.
And likewise, it should take longer time. So in this case, I think it's from 1 to 2 in the good scenario and 3 to 4 in the bad scenario.
And those dash,
This yes, for simplicity, load 1 and yes. These are simple examples, so I just he can choose 1. And the model is like this. We define the voltage assignment with probability problem as follows. This 4 is given. M different voltage level, V1 to Vm, and the data flow graph is the task graph, G. M is the task, ED is the edge with TPE for each load executed on each voltage E. This is also given. And given the
T means time, right?
time,
This
P means the probability.
probability.
This E means the energy.
And this E can be different. That's what you said. Even though in your example you assume there
Yeah,
but
yeah.
in effect, that's what you
Yeah,
realize
yeah.
usually it can be
Yeah.
different. Okay.
And then also given the time constraint L and the confidence probability P.
And this time constraint is a hard constraint or soft?
I think they are soft constraints.
Meaning that
Under the probability.
I can finish
Yeah.
overall in 3 seconds. Or
Yes.
10 minutes.
Yeah.
And maybe with probability of 1, it could take longer.
Yeah. And now we need to find an assignment of voltage level for the load. There are two requests. First is to minimize the total energy cost, and the second is guaranteed probability satisfy timing constraint.
I think item 1 is like the objective function. Item 2
This is a constraint, yeah. And we use the dynamic programming to solve this problem. The key is to build a table, like this table, for each node, and each time constraint. Like this, for example, the time constraint 5 time units, we can finish the job at the probability 0.4 and consume 4 energy. This is the table. So if we have the probability 1 to finish the job and consuming 4 energies, we need at least 7 time units. This is the table. So we use the dynamic programming to build the table. This is the result. Any question? This is for load 1 because the load is a task is a sequential. First finish 1 and then do the second. This column is this load is the load 1 could be finished on the constraint, and because when we need to finish the load 2, and we need at least 2 time units because use this and time 1 and 1, and the probability is 0.09, and the energy consuming is 8. How to build the table? First, we need to build the cumulative distribution table like this. For load 1, we can finish the load 1 in 1 time unit, and under the 0.3 probability and consuming 3 energy. This is the mean. And at 2 time units, we also, because this is 1 unit and 3 units, so at the 2 units, we also need 3 energy consuming and the probability 0.3. And if the constraint is 3 units, so we can finish it 1 and consuming 3 energy, because this is the cumulative distribution of the probability. And the second is also
Do you have a way to write down the objective function in different stages so that it can show the program?
Use an analytical formula.
Well, close for analytical form. For instance, if here, because this is simple example, let's say
Yeah.
I change this E energy to, for instance, maybe 1 and 2, then we'll basically how your algorithm will operate. And also if we announce it's the integer, if I add not for 2, then what will happen?
Yes, in the program, I can calculate analytic.
This table is unclear, for instance, what are different stages. Like here, I know that you, for instance, your time is integer, so you numerate 1, 3, 4, but that's very exhaustive. If I do have some completion time, like for example, 2 seconds, which you'll have to consider about that in different nodes.
Yes.
I'd like to see like some generic formulation how the dynamic program is solving the problem.
This is first build the cumulative distribution of the knowledge, and now we can compute the table D like this. And for example, if we need to compute the table like this cell, and the time is 3, time constant is 3, then the node T1 and the node 2 is 3. There are two cases. Case 1 is node 1 use 1 unit, and the node 2 use 2 time units. And the case 2 is node 1 use 2 units, and node 2 use 1 time unit. Then we can calculate, use the equation, use this load. This load means like this. And because the node 1 is 1 is like this, and the node 2 time constant is this. So we can calculate the table, the D23, use this equation, can get it. And on case 2, is also can get this value. Then compare these two values, the second value we can remove because we can finish it use full energy consumption under 0.12 probability. It is better than the consuming 6 energy under 0.09. So we can remove it and can get this cell. This is the step to get the D table.
From this table, do you know, for instance, what multipliers one and 2 to operate over achieve such probability at completion in 4 seconds with probability of 1?
I'm sorry?
I mean, from when you say that this 6 with 0.09 probability, the mission will be completed in 6 seconds, that can be removed because it's inferior to this 0.12 probability, the mission can be completed in 4 seconds, meaning that you have shorter time with higher probability.
No. Not short time. It's at the same time, 3.
Okay.
And this is energy.
Okay, you assume you can use with higher probability, you can use smaller energy
Yeah.
to complete this mission in 3 seconds.
Yeah.
Then that choice should be better than the other.
Yes, yes.
But when you put that into the table, it only shows that, yes, I can use phone like maybe energy phone to complete the mission in 3 seconds with probability 0.12.
Yeah.
Doesn't really say if the corresponding operation procedure, like you need to choose node 1 to operate on voltage,
Oh,
1 and node 2 on
yeah.
So because that's unclear.
Yes, we first, yes, in my program, I also can remember the voltage because I choose the table, the cells. We can also need have another the variable to remember the
You need to
voltage.
memorize the state of how you chose the actual node voltage and the execution procedure in order to achieve this probabilistic guarantee.
Yes, I have another table to, if we choose this, I have another table to corresponding to another table to remember the voltage corresponding to this cell. This is the process to build the table. And this is my algorithm. It has 2 parts. One part is the offline part, and another is the online part. The offline part is build the table of energy and the B table, and calculate the D table use this algorithm.
What do you mean by the online?
Because yes, this is offline. The second is online. Because the table we can get.
I assume this is offline for sure, because you just say, well, if I take node 1 and operate on voltage V1, with this probability I can complete in 1 second, that probability I can complete in 2 seconds. Online means when you really have a job, you know in 1 second you finish. Then there's no uncertainty about that. Right? Because I'm a little confused about the definition of online algorithm.
Online is if I have built the table, then on each node we can search the table could scale the voltage if under the constraint time. We can.
But when you say online, do you actually know the execution time when you assign an optimal sequence, like whatever you're using the programming or some other algorithm to each node?
I'm sorry, what's the question?
Well, I guess the question is when you say I have an online algorithm, does that mean you actually know the execution time so that you say, okay, so based on this sequence, I chose node 1 on voltage V1, node 2 on voltage V2. And then I would expect with probability 99% it will finish in 4 seconds, for example. And then when you really run your operation, you know either it finished or it doesn't finish.
Yeah, this is the soft constraints. So it is, if we finish this is a probability and cannot fully guaranteed. So it is a soft.
Well, from the pseudocode, it's actually
Hot.
Like, what do you mean by scale voltage? So that means, like, you change your selection after you see certain node already completed the mission. Like node, after you see node 1 already finished in 1 second, then I say my node 2 should choose V2 instead that we want. So that means that to me that's like online. Because not like probabilistic, you say, okay, so 9 out of 10 times it will finish in 1 second. Otherwise it will finish in 2 seconds, 3 seconds.
I can step by step to because for each node I use is
Once to ask a singular thing, right?
first because we have built the table, so when a task input, then we can use the time constraints. We set current time is to 0. Then for each node, we do the time, search the time at the node. If the t is the constraint of the time, if the t is greater than the constraint, then we could choose.
Is a true execution time that already chose from node 1, operating as a logic.
Yeah.
Well, how can you scale the logic? That's how you answer it. You mean likewise that node 2 has 2 choices, V1, V2. You change that, you say not V2, I can make it V3 instead of V2.
Yeah, I change the voltage level and search the table.
So would that be a different optimization problem?
Because the optimization problem is to build the table, and then it is not. It is the application of the table. And then I use another example to test the program. This is more. It is also simple example, and the result running the program and use this example is like this. Then the constraint is from this table we can select at 16 time units we can finish at probability 1 and use the energy
I
level.
don't know what the actual operation will choose that. And also
You mean the voltage assignment?
yes.
Yeah. I didn't put the table, the voltage assignment in here. Yes. In this algorithm, we can remember the voltage.
Well, actually, I think I probably should have, but do you propose this? I mean, I know this may be part of your previous research, but I mean, for this dynamic programming algorithm to be implemented in this particular way, is it like your contribution, or I mean, someone already proposed that, but you made some modification to this problem?
Yes, my previous advisor, he also provided this algorithm, and I just implement it.
Well, I mean, it's unclear about actually the description of dynamic programming. So that's why I'm asking for instance. It would be nice that you at least reformulate it in a cleaner way that people
I also program this problem and do some simulations like the result like this. And if we also can further work is to the probability, because we know the probability is the discrete And the future work is could use the continuous probability of this.
That could be like I'm saying that even for the time, if it's not integer, then your table will be a disaster.
Yeah.
You need to literally enumerate all the possible combinations, all the possible consequences, and also those tiny probabilities or whatsoever. Like
Yeah.
actions. That's why I'm saying that, for instance, you can eliminate some unlikely operations just simply because you know, for instance, one action is definitely better than the other. But in an all continuous probabilistic setting, you cannot do that.
Yes. This data is from some experiments and could get the. Yes.
From the real embedded system design or
This the data we cannot get. I just use this data is made, but in real embedded system, some another researchers can get maybe.
Well, this table, what does
Hmm?
in that case, what does those columns mean? I think
This
the second to the
this
I think here is the probability and here
here is energy.
you have this different columns. The P is probably, I know P is probably.
yeah, if you have larger energy, which 44 probably means a different set of voltage level you operate on those
Yeah.
nodes, then you have higher probability to complete in 5 seconds. That's my reading,
Yes.
right? So this table could be huge if you think about all the way, all the combinations of different setting actions, assuming they can complete at different times with different energy. You need to exhaustively enumerate all the combinations in order to find out what's the best way to do it.
Yes.
And then if you have a practical problem, you say, I want to achieve something like this mission in 10 seconds with probability higher than 0.9, then I need to look at this table.
Yes.
Again, for this row, and then saying, okay, that's the third row, right? Sorry, the third column. And then I need to still find out from what would be the actual voltage
yes.
assignment and the action sequence
Yes.
for node 1, 2, and 3. That's why I'm asking about the complexity of doing this. I think that if you want to go for continuous distribution, literally no way you can handle
Yes. For continuous, this is harder, I think. And this is a reference of.
that. I guess I asked a lot. I know it's getting late, I apologize. But I just hope that some part of the engineering applications might motivate you to look into what would be a better way of site optimization techniques. Okay, thank you very much. One more, right? And we'll have more evaluation sheets.
Dr. Chen, I think since we're a little late, we should have a penalty function applied on the exam that makes it easier.
Okay, I will try. At least the grading part, you can see, you may want to suggest some curvature function to make the optimization a little bit amenable.
I think zero would be more good. Everything non-zero equals 100. Everything.
Well, and another motivation would be, for instance, putting some extra credit for those who seriously consider revising your project report based on some comments. Say, I hope that I will finish this and post on Blackboard. Okay, so Xu will present another bioinformatics application called inference proportion to the splicing epitopes.
Hello, everyone.
my term project is about the inference proportion of splicing S forms. And first, I will introduce the background, and then I will talk about the method using in this project. And finally, I will show you the simulation results. And first of all, this project is related to the RNA-seq technology. And from this figure, we can see the messenger RNA is purified and fragmented into the cDNA library. And a lot of short reads, RNA sequence short reads are generated from the cDNA. And then we need to use some software to align these short reads back to the reference genome and to estimate the gene abundance score. From these slides, we can see this pre-messenger RNA has 4 accents, different accents, and then these accents are alternative spliced into 2 different messenger RNA. And the first messenger RNA doesn't include the yellow axon, and the second messenger RNA doesn't include the yellow axon. And then these 2 messenger RNA are translated to protein S forms. So our goal is to detect the proportion of these S forms. And how to formulate the problem to the optimization problem. And at the beginning, we need to formulate, we need to construct the relationship matrix between the S forms and the axons. I use the same example. The first column corresponds to the first S form. And if this S form includes this axon, then we set this position to 1. Otherwise, we set to 0. So this matrix has 2 columns. But I suppose here the length of axon is 1. So in the real case, the length of axon is more than 100, sometimes is more than 10,000. And this matrix S is very important for us to detect the proportion of S forms. And I use this example to show you how to formulate the problem into the optimization problem. Here we have 5 copies of S forms, and the first S form has 3 copies, and the second has 2 copies, so the proportion is easily obtained. And but this part are hidden for us. We don't know. This is ground truth. But we can observe the these axons. For example, this red axon is 5 because we put this copies together, and then we can observe this is 5 and the yellow is 3 and 2 and 5. But we need to use some matrix decomposition method to decompose this observed data into 2 matrices. But if without any constraints on this decomposition, then the solution is not unique. So we use this. You can see this matrix is here, is 1, 1, 0, 1. And then you can find that this has the same structure, but the number is 0.6. That means this is the proportion of this S form. And the second column is same. And then this matrix, because here I just use one sample. If I have many samples, then I have many columns in this two matrices. And so this number of value is the total number of copies of S forms. So this is our formulation. And then we can formulate the mathematical framework. And this is our observed data matrix E, and then we need to decompose the matrix E into W and R. The W, this is our relationship matrix, and this non-zero is corresponding to the proportion of S form, this S form. And if we have L S forms, so we have L column. And here we have N samples, and this column corresponds to the total copies of this S forms of in this sample. And then this is the noise. So we need to minimize the noise. So this is our constrained convex quadratic problem. And this is the constrained condition. We need to sum up all the proportion equal to 1, and the proportion should greater than equal to 0. And we can equivalently formulate to this form. Okay.
So your matrix W, some elements of your matrix W are 0, right?
Yes, yes. Because this S form doesn't include this action, so we set this to 0.
But my question is, I cannot state which element should be 0 and how many elements should be 0.
That simply knows, because it's
This
like one isoform contains certain accents or accents, right?
Yes,
and
yes.
That's something you have to know.
So you know the structure, you know the position of those 0.
Yes, yes. So this is from prior knowledge. This is from prior knowledge.
But
Yeah.
still, those p's can be 0. For instance, this isoform, this isoform doesn't participate in that expression. That's likely, right?
Yeah.
So that means the constraint only this pi is greater than or equal to 0.
Yes. Yeah. Yeah. It's clear. Okay. And then we can formulate into vector form, and the vector z is part of all the column of matrix E, and is same to H, and the X corresponds to the proportion of these S forms. So this is the constraint conditions. Any question? Okay.
So finally, the problem is formulated as linear constraint.
Yeah. Yeah, list square. So we can get the global optimal solution to the equality constraint least square estimation problem, and this is the solution.
But not exactly true, because you have non-negative constraint, not just linear constraint. So this projection is only for the linearly constrained least squares. Doesn't guarantee you that when you project your standard least squares solution to the affine transform of the hyperplane. The subspace in your constraint set still is most automatically satisfy the non-negativity.
So you mean this solution cannot guarantee the X non-negative? Oh. Okay. But
Definitely it's solvable. And it's common program. And also
Yeah.
it has quadratic program.
yeah, yeah. I use the MATLAB function to solve this problem, because, I finally I will show you the simulation result. I use the real gene and the ELK4, and this gene has two isoforms, but actually many genes, we have 20,000 genes, and some gene has more than two isoforms, some more than 20 isoforms. I mean, so I just for simplicity, I just use the two isoforms, and the first isoform has 5 axons, and the second has 3 axons, and we need to calculate the length of axon. For example, this axon is the first of axon's position. This is the start position of the first axon, and this is the end position of the first axon. Then we can calculate the length of axon. And this is our ground truth. I assume the first isoform, the proportion of first isoform is 30%, and the second is 70%. And then this is our observation data, and this data has more than 4,500 rows and 5 samples, and and this is our relationship matrix, and it has same more than 4,500 rows and 2 columns, because 2 isoforms. And this is our result. When I add some measurement noise on the observation data, and then I run my code to get the to calculate the proportion of these isoforms, and this is the second isoform, and we can find some of results are not very close to the truth, and I calculate the Frobenius norm between the truth and the calculated proportions, and the norm is 0.02, and when the variance is reduced to 20%, and the Frobenius norm is 0.008 about, and we found the result is better than the previous.
Even your previous plot, I think that's good enough for your inference problem, right?
Yes,
I mean,
yeah.
You can really achieve the proportion estimate down to like 70% versus 30%.
Yeah.
Proportion. I think that's good enough.
Yes, yes, I think because why the result is very good, because the row is very large.
And also you only infer 2 isoforms.
Yes, yeah, that's the reason why the result is very good. And when the variance is 5%, the Frobenius is to 0.002, and the calculated proportion is really close to the truth. And the conclusion is the method based on the depth is a very lower way, and is more accurate than the previous method, because in our previous research we used the RPKM, and that dimension is very low, and the result is not very ideal.
Here, when you say depth, that means
Depth, here.
the way to generate.
Because I just say that suppose the length of axon is 1. So because the length of this axon is 530 8. That means this is the base. You can see I omitted many rows here. I will show you here. Yeah, this is our observed data, and you can see this is the first base of this axon, and then we have many other signals here. In rest of.
Like the starting point of the axon.
Yes, yeah.
To count like the sample.
Yeah, yeah.
The sample like the number of reads per sample. Over total sample. But here 32 is what like we.
32 means the.
For each sample you count like how many.
How many counts at this base?
Appearance of the axon 1 starting from 1 that you actually see that, right?
Yeah. Do that. Okay.
Iteration in the axis. I thought you show the result in your analytical solution. You can constrain this square solution.
Oh, I run this 30 times.
Oh, so this is
Yeah, and each time I add some noise.
That's not really iteration. It means that, for instance, you have this observation plus some noise, and this noise you just say because it's random, so you do many Monte Carlo simulations to see that if you get the same result. That's what you mean.
What's the Monte Carlo?
Well, it's like, for instance, you say you still have the isotone structure, but you plus some noise in actual observations, right?
Yeah.
And then, of course, because noise is random, then you do many different runs.
Yes, yeah.
And that's what you call iteration. But in fact, it's not a real iteration in your algorithm. Well, it's not really an analytical solution. Okay, so, yeah, just maybe, yeah, 2 more minutes.
I still cannot understand what is your point.
Well, I guess his question is whether, for instance, this iteration 5 and 10, really like 10 usually depends on the results from 5, but in your case, it's just you do experiments for many times, like for 30 times.
Yeah.
And you display the estimated results.
Yeah.
Right?
Yeah.
Okay,
It's independent.
yeah.
Yeah.
So that's what you call Monte Carlo simulation, because it's based on random experiments, so that you want the results on average to be reliable.
Oh, okay. Okay. Thank you.
Any other questions? Okay, thanks a lot. And of course, sorry about the delay, but I think at least I enjoyed a lot of these talks, and actually also learned some of the research problems you guys presented. So bear in mind that the final exam will be next Thursday around